So let's start. We can so be on schedule. So we are gonna start with a few words by Elias, with the head of the, and also thank you very much. Interest on this course and register to attend either.
Thank you very much for coming. I'm very excited to have a course on how to integrate nature into economics. For me, it's the first time that I ever attend a course. And, the reason here, at least, is I feel that we have a huge accumulated debt application. Application that models all economic phenomena except for nature. I guess the assumption is that nature is just so large that it's kind of irrelevant. But I'm sure that everybody sitting here realizes that that's not true anymore. And the course that we're gonna be discussing this week, in my view, essentially allows us to do three things. First, it allows us to evaluate the value of natural capital, and that goes a long way into trying to get nature into our prices, which is the main thing that is missing. Secondly, once you understand how to value nature, you can, so to speak, do comparative statics. You try to figure out how different policies would affect the value of different ecosystems. And that's something that is sorely missing in our public policy design. And third, and this is more for central bankers in the room, I guess, we are also going to see applications in which this method of evaluating nature can be embedded into a model of macroeconomics. And that is very useful because that allows us to essentially forecast the future, but with nature in it. And I am absolutely sure that when we start forecasting the future with nature in it, it's going to look a lot different. And this is something that we need to understand and react soon. That's why, at least from the part of the central bank, it's always, or it has been for a number of years, a very high priority on our list of things to do. And I'm very happy and honored that we're going to have a course on this subject by such distinguished professors. Because you guys need to understand this. There are like 5 people in the world that know how to do this, and 2 of them are sitting here, right? And the idea is that after that, there will be more people, right, that know how to do this. So, having said that, Pancho.
Yes, already said everything. So, I'm Francisco Gallego. I am professor of economics and the director of the Institute for Sustainable Development. I want to do some advertising. So this is like a new academic unit in the university where we have people from different departments, for biology, econ, Felipe Fortanis the professor and young professor from the business school, the sociology, and many other places. And this is very important for us, because I think this shows how we can, as from the university, learn new things, apply it to new research, new classes, using like interdisciplinary research. Also, in a joint venture with the central bank, with policymakers. This started, I guess, like 1 year ago, walking from here to the subway station, talking to Elias, and we're very happy to have, this class. So Elias already mentioned like the contents of the class. I just want to finish like thanking like the organizers, from the university, Felipe Jordan and Alejandro, Gonzalo, and Antonia, and the central bank, like the IADB, the speakers. So we're very happy to have here, and just let's start. Thanks a lot.
Good morning, everyone. Thank you very much for that introduction. Yes. It's a real pleasure to be here with you today. My name is O'Neill Banerjee, and I work with my consulting firm, RMGO Consultants, and I've been doing so for the last 1.5 years or so. Prior to that, I was with the Inter-American Development Bank based in Washington, DC, working on operational projects in rural development, agriculture, tourism across Latin America. Before I go too much into that, I want to make sure that I introduce my colleague Justin and have him say a few words. Justin's going to be taking over after an introductory session today, and he'll be speaking to theories, mechanics, and application of Invest.
Hi, everybody, and thank you also for that wonderful set of introductions. I'm so pleased to be here. I'm Justin Johnson. I'm an assistant professor at the University of Minnesota in environmental economics. And yeah, I have really been focusing much of my career on ecosystem services, and in the last 5 years, been narrowly focused on how to integrate ecosystem services and macroeconomic models. And so this really is the culmination of a lot of work that I've been doing. So it's so fun to see this many people interested in it, as well as the hundreds apparently of people online. And so I'm excited. I think this is going to be a great set of days here, and I look forward to talking more. O'Neill's going to be taking us away, but I will be spending the latter half of today leading us through the mechanics of running ecosystem service models. Just a preview of what I'll be saying. But for now, back to O'Neill.
Just sharing. Anyone know what I should click here? Okay. Oh, what's? Yeah. Perfect. Okay, we're gonna put here so we go around. Suppose my good side.
Yes. There's another one there.
Thank you. Okay. So, right. My name's O'Neill. I'm based in Jakarta, Indonesia now, actually, which is where I work from. I continue to work on this integrated modeling. So integrating macroeconomic models primarily computable general equilibrium models with land use and services. So we work with the American Development Bank, the World Bank, USAID, various other institutions, essentially developing this NEEM integrated economic environmental modeling framework for other regions of the world. So being at the IDB where we developed the NEEM framework, now we've been taking it outside of the region. So we have a lot to go through over the next 4 days. And this is the first time that we show the full integrated framework with ecosystem services modeling with the NEEM model. And in addition to that, we have hands-on exercises with Justin, application of Invest suite of models, and also Justin for the future, and the linkage between GTAP, a global CG model, and ecosystem services modeling. Typically, when we deliver training on NEEM, we start with a week of full days to get the basics, the concepts, the theory. Near the end of the week, we start with applications through an interface that we've developed. And the following week, we get into more applications, hands-on, working through different policy and investment scenarios. The person that I've been working with on this since the very beginning, since 2013, when we started this project, some of you may be familiar with him. He's quite well known in the region, working with different institutions of government, showing these tools, particularly computable general equilibrium modeling. Unfortunately, he's the closest one to Santiago, but he's the one that could not come. He will be joining us beginning tomorrow, and he will be with us for all of the session. And we'll be leading the hands-on application of via satellite. So the objectives that we have for the workshop, essentially, so to show you this integrated framework that's really comprised of 3 parts: computable general equilibrium model, a dynamic and recursive dynamic model, a spatial allocation model, a spatial land use site cover change model, which then provides us inputs that we can use in the ecosystem services model. So we'll show it at the single country level, which would be EAM plus ESM is what we call it. And then the global level is the use of the GTAP database, the GTAP model, and the linkage with the Invest suite of models. And in the middle there, a land allocation model called SEALS, which Justin has been all about. So gauge familiarity with each of these components. And so there will be a hands-on section on EAM itself. There will be a hands-on section on Invest and various ecosystem service models. And then we'll also show you some different models that we use for land use site cover change modeling. So this is the necessary bridge between these modeling frameworks. So we'll show you Dynaflu, what we use for the single country work. And Justin will also be showing you, I believe, a scenario modeler that uses sometimes in these sorts of events to demonstrate modeling scenarios with Invest. So in addition, gain practical experience in applying ES models. I'm trying not to use too many abbreviations, but there are some key ones. Basic simulations with EAM. And then at the end of the day, like I said, this is typically something that we do over multiple weeks. And this is going to be kind of, an overview of the modeling system. But we want you to leave knowing where you can get more information on each of the components. So if you want to further, if you decide, I want to do this macroeconomic modeling, I'm not so interested in the other things, you know where to go for learning more about it. There's a lot of materials that we've developed, that the Natural Capital Project has developed, that are freely open and accessible. So we'll point you in the right direction to that. So, like I said, it's Martin, myself, and Mark Horridge, also one of the founding fathers of large-scale computable general equilibrium models. Renato Vargas, some other colleagues from the IDB that have been pioneering these methods there for the last 10 or so years. EAM is something that we've used within the institution of the IDB in terms of project evaluation. So running the model to generate results that we then use in cost benefit analysis for deciding whether or not to fund investments. So as this is the first time we're presenting all of this material at once, we're going to be a bit flexible in terms of the flow of things. So we want, there's a certain logic to things, but we're going to jump around a little bit so that you're not doing one thing for too long. We'll be flexible. The agenda might change slightly, but I mean the core that we're going to cover is all written there in the agenda. One thing that we've done that I consider to be kind of special for this workshop is that very recently, well, till yesterday, we've been developing a new application for Chile. So Martin has been working hard on updating the database, updating the model, and implementing these scenarios that we've designed with some of the colleagues from the central bank. And what we're going to focus on are the nationally determined contributions. And in fact, looking at the country's NDCs is something that we're doing quite a bit for the World Bank. So we've been working with them in India and Thailand and Cambodia and a couple of other countries, looking at their NDCs as part of their new CCDRs, climate change and development reports. You'll see these are new reports that they've been releasing for the past year or so. Indonesia's was just released the other day. And we've been looking at these NDCs quite a bit, focusing on agriculture, forestry, and other land use. So I'm not going to go into huge depth on what we did in this application today, but we're going to go into it tomorrow. I'll provide a solid overview of the application to Chile. And then Martin is going to walk through all of the steps involved in implementing those scenarios in the interface. So essentially, in the case of Chile, the main targets for FOLU, forestry and other land uses, is reducing deforestation by 25%, and this is with respect to a reference period somewhere between 2013 and 2008. We'll clarify that later on. And in addition to that, increasing afforestation, so planting trees, as well as restoring degraded forests, both by 200,000 hectares. So in addition to whatever reduction there is with respect to a baseline level of deforestation, we'll be increasing tree cover, well, by 200,000 hectares and restoring forests. This is the first integrated application to Chile, so it'll be interesting to see what you think about it. And we're looking forward to working with you in defining those scenarios as best as we can to represent what the real policy directive actually is. So I'm going to speak to that just for a few more minutes, but then I'm going to give you an overview of EAM. I'll go through some CG and EAM modeling basics. CG, a recursive dynamic model, is at the core of EAM. It's the starting point. And then if we have time, we'll look at this case study application of EAM applied to Sustainable Development Goals in Guatemala. And in this case, this application doesn't include the spatial modeling. So it was what I am attempting to convey is the phased approach that we took to develop what EAM is today. So let's see how we go with respect to time. I want to make sure that we stop at 10 a.m. So this is a quick overview of what this integrated framework work looks like with the three modeling components. So we begin with the policy questions. So we started as CG modelers, and our approach has always been one of looking at the policy question or the research question first and implementing that in the CG framework. Calibrate EAM, so we look at what the most recent information is from the system of national accounts for our country, specifically the supply and use tables, integrated economic accounts, household survey data, among other things. We run a base scenario. So the base scenario is essentially a generic projection of the economy. So we're looking at projecting the economy based on expected GDP growth, which we usually get from the country or from the IMF's outlook. project population growth and derive from that labor force growth. There could be some changes to stocks of natural capital in that projection. But what we want from this baseline projection is essentially a projection of the economy that, how we expect the economy to evolve without any major policy or investments. So we run the base and we run the scenario. So in the case of the NDCs, we'll go into detail of the different aspects of the scenarios tomorrow, and essentially increasing the area of forest that is planted. And then some proportion of that is then used for commercial productive purposes on a sustainable basis. Restoring forests and reducing deforestation, as I mentioned originally. So there's two approaches here. There's one simpler approach and one more complex approach. And the more complex approach is actually what we've been implementing most. But now that we've started working in this NDC space, land use has been primarily determined exogenously. So the scenario defines what our expectations are for cropland, grassland, forest plantations. First, I'll speak to the more complex framework, where essentially we're running these scenarios. EAM generates a projection of demand for land. That demand for land is spatially allocated across the landscape. So we usually have, we either work at the national level or subnational, so regional in Chile, for example, state level in the US, etc. So we have state-by-state projections of land demand for a period. We run this on a periodic basis, typically 5-year periods. We allocate this demand for land with this Dynaclue land use land cover change model developed about maybe 20 years ago by Peter Verberg and his colleagues currently at Amsterdam Free University. So we spatially allocate that demand for land for the first time period. And then we use those maps, those projections of each component of the scenarios, and then the joint implementation of all of those policies. We use that as inputs into the ecosystem services modeling. So we use the INVEST suite of models developed by the Natural Capital Project, Justin's group, one of the groups that he's affiliated with. Then we model typically 5 or 6 different ecosystem services. Now, what we expect is we could just do this one-way framework workflow and call it good, but we expect that change in ecosystem services flow should have an impact on the economy. Running this on a periodic basis allows us to capture that effect on the economy. So what we do is, after this 5-year period, we develop an economic shock based on changes in ecosystem service flow. So what we'll show in the case of Chile is how erosion, for example, affects agricultural productivity. There's a known relationship between agricultural productivity and erosion. In the literature, the magnitude of the effects of a change in erosion with respect to agricultural productivity, there's a broad-based literature on that. When we look at that literature to calibrate our economic shock, that's what we do in the case of erosion. Similarly, for the first time, we've been looking at pollination services and looking at change in pollinator abundance. So using the INVEST ecosystem service model, looking at how pollinator abundance might change with our scenarios. So if we're increasing habitat for pollinators, we might expect abundance to also increase. We also know that there's an effect associated with, there's a productivity, potentially a productivity effect, essentially, agricultural productivity effect associated with changes in pollinator abundance. And so when we look at that literature, again, there's a not such a broad literature as there is in the case of erosion, but there is some literature out there that allows us to calibrate the shock and then implement it in the economic model. And so we do this 5-year steps. So every 5 years, we rewrite EAM, generate a new projection on demand for land, because that shock that we're introducing in the economic model is affecting the decisions of producers and consumers, and thus affecting land use in periods. So we run this iteratively until we get to the final period. And then at the end of the day, what we're able to say is that the value of erosion mitigation services is X. The value of pollination services, crop pollination services is Y. Get this, we estimate this as the GDP impact of that service. So because we are not using any values derived from other methods outside the model, like stated preference work, willingness to pay, etc. These values that we estimate for ecosystem services are entirely consistent with the system of national accounts. So what this lends, in my view, to the exercise is credibility. Because we're not using, benefits transfer of other studies from different time periods, etc. These are perfectly sound methods, but our approach ensures consistency with the system of national accounts, and there's a certain additional credibility associated with that. So I'll go a little bit more quickly now. What's the motivation for the EAM platform? So this is what we call it, the EAM platform, decision-making platform. It integrates macroeconomic models with the environment. So CG models are widely used in generating evidence of public policy. Like I mentioned in cost-benefit analysis, there's a few models that are better documented and have such a large literature as CG models. Various institutions like the IDB, Ministry of Finance, central banks, IMF, they either undertake their own CG analysis or they contract it out. You're on board with CG modeling, if you don't have any huge reservations, then you'll like this quote. In all cases where the repercussions of proposed policies are widespread, there's no real alternative to CGs. So this is saying essentially that when we have economies that are multi-sectoral, with these interactions between sectors that are important, where if you impose a tax on the transport sector, this is going to affect the agricultural sector, which is going to affect the income of rural laborers, etc. Where there are all of these interconnections, there's no other framework that captures it as holistically or as robustly as the CG model. Not to say there aren't limitations and disadvantages, but it's the appropriate framework when we're concerned with all of the. So the issue that we set out to address, essentially when I arrived at the IDB, having worked with these models in my time in CSIRO in Australia, for example, Brazil, is the fact that natural capital and ecosystem services are almost absent. You'll find applications that are forest sector specific or water sector specific, but what was lacking, at least with regards to those services that have a market price, is a framework that is consistent and includes all of these different interactions. So a policy that, for example, stimulate the agricultural sector could have devastating consequences for example, for water availability for other consumptive uses, for example. And these sort of features are absent from a traditional CG model. A minute, so I'll just play this. This is essentially an overview of. That's fine, doesn't matter. I'll show you where you can find it. So EAM early development at the IDB. So as I mentioned, this all started at the IDB, and the research challenge was, how do we integrate ecosystem services into a CG? That was the basic question. Those familiar with CG will know that we're not able to capture transactions where there's no, we're not able to include goods or services for which there are no transactions. So a good needs to be sold, and it's bought by someone else in another agent in the model, but that income needs to be earned from some source. So simply including an ecosystem service and what we assume to be its price is not an approach that is allowed in this kind of consistent framework. So at that time, the System of Environmental Economic Accounting was published. So this was in 2014, we started in 2013. And I mean, this has been decades. The System of Environmental Accounting, of course, those at the central bank will know that it's a framework that's consistent with the System of National Accounts. and CGE models being built on the basis of data from a system of national accounts. This makes it extremely, well, it's almost revolutionary, but the sort of information that we can now include in CGs in a way that's consistent with the country's system of national accounts. So our first step in this process then was to include data under the CIAs, environmental economic policies. What we developed was the EAM conceptual framework. We published a paper on that back in 2016, which laid out what we felt was how we could integrate this data into a CIA, into a SDG framework. In this process, we developed natural resource or environmental modeling modules. So these effectively capture the dynamics of natural resource sectors. So for example, the forestry sector operates differently than the textile sector because we have growth of forests, we have deforestation, we have sustainable versus non-sustainable use. The mining sector where we have new discoveries, so increases in the stock of mining resources. We have potentially increasing efforts required to extract minerals when stocks are in decline. The fishery sector, for example, where we have growth, sustainable catch, and all of these concepts we're familiar with from sort of standard environmental accounting. We built these natural resource modeling modules into the EAM framework. So our model, and we'll go into this in more detail, in particular Martin will speak to this, is that our model, the theory is separate from the data. So the model, there's only one model, the EAM model, but what changes in each country application is the database that underpins that model. So it's a generic modeling framework that has all of these capabilities built in, that's transportable effectively across countries where the supporting data exists. So we had a number of applications looking at SDGs, which I'll speak to in a minute, forest and fuel wood also in Guatemala. Once we had this down, the next step then was to link EAM with ecosystem services. Here, that we learned a little bit by doing, so we knew that we wanted to get there. So the CIA effectively takes care of those ecosystem services for which a market price exists, and provides additional information on quantities. So for example, cubic meter of timber, megaliters or gigaliters of water. Natural resources in quantity units, also in dollar units. But to capture those ecosystem services that don't have a market price, we needed to make this linkage with the ecosystem services modeling. And at that time, I was involved with a SNAP, Science for Nature and People Partnership project while at the IDB. And I met Kenneth Bagstad there, and we started working on this idea. And I said, look, so for this Rwanda project that we worked on together, the SNAP project, I said, look, we have our EAM generated demand for land. Take this and do your ecosystem services modeling. What we learned was that the ecosystem services modeling doesn't do the land use land cover change modeling for you. So this is another step that we needed to build into this whole process. And so at that time, we were working with a colleague, a very old friend of mine, Sebastian Dudek, and he helped us build an application in ArcGIS with Model Builder, which would take our EAM demands for land and spatially allocate them according to some predefined rules, user-defined rules. So we thought we were off and running, but we weren't entirely satisfied because we knew that there was a large literature on land use land cover change modeling that we wanted to make sure that we were integrating into our modeling framework. We wanted to integrate the best science into our approach. So we started studying that literature as well to figure out how we could improve that bridge effectively between EAM and the spatial ecosystem services modeling. So just quickly, what's the value added of the EAM approach? So EAM, just like any other CGE model.
We can ask a question, right?
Sure. Yeah.
So I'm completely ignorant, but I thought an issue with the computable general equilibrium model was that also the dynamic part that we typically see in macro models were absent too. Am I wrong, or?
CGE, there's either comparative static where it's just before and after, or there's a few different approaches. Another is recursive dynamic, which solves the model on a periodic basis. So every year, essentially, till the end of the time period, we'll simulate to 2050. And then there are forward-looking models that where households have perfect foresight. But the most common form of CG is either recursive dynamic or comparative static. Yeah. So this is kind of why I say future looking, because it's not forward looking in the economic sense. So we're always asking questions about the future. What if we implement this fiscal policy? What would happen to household income, et cetera? We've integrated the SIA, which covers off on market ES, the natural resource modeling modules that I spoke to before. We have the standard economic indicators that many are concerned with, ministries of finance, line ministries, central banks, so GDP impacts, employment, sector output. But we're also able to speak to impacts on natural capital and wealth. So wealth is an indicator that we calculate with EAM, which is essentially adjusted net savings or genuine savings, which takes net national savings and adjusts it for changes in stocks of natural capital and environmental quality. Link EAM with a microsimulation model. So many of the people that we worked with were interested in distributional impacts and poverty, and a standard CG doesn't capture that very well. So we've linked EAM with a microsimulation model. And then of course, we've linked EAM with the spatial land use and cover change and ecosystem services model, which estimate impacts on non-market ES, both in value terms and biophysical terms. So quickly here, what are we up to? So as I mentioned, we developed EAM while I was at the IDB. So we have almost complete coverage of Latin America and the Caribbean of EAM models that are freely available to download. And based on the latest database available, so systems of national accounts, supply and use tables are the key for the EAM model and CG models in general. So we use the most up-to-date information about 3 years ago, essentially. So we're now expanding coverage of EAM. So you can see we're in India, Indonesia, Thailand, Cambodia, Zambia, and many other countries. One area that we're really working on a lot is enhancing the linkages between EAM and the ecosystem services modeling. And this has been done for pollination and erosion. We're now looking at, we have been looking at water purification. And then there are a couple of others that we're yet to tackle. So this essentially, the approach involves understanding the literature so that we're able to make a linkage between the changes and economy, developing rules of thumb for this. Often we're working under very tight timelines. We need to deliver in a matter of 2 weeks, 3 weeks, 4 weeks. We need to institutions that we work with, and the Open EAM platform. So the IDB is hosted at the IDB. There are all sorts of resources. I can show you what you can see there. So if you have a look at it, if you have questions further down during the week on Friday. So with this, the idea of making all this open is that we're able to develop policy advice opportunely, so quickly, but also that we can focus on innovation, because when I arrived at the IDB, I saw so many models being replicated. Same thing. Oh, we need a CG model. Okay, well, $30,000. But it's effectively the same CG model. That replication of effort was annoying for me, and for this reason, we wanted to make all of this information available publicly. At least it was one of the reasons. You want to know how I can show a website up here? here how I can go back and forth.
Ya, sí. Pero como invitado, o sea, como así.
O sea, como técnico, como lo vemos que.
Claro, pero me sale. Ah, no, me sale, quizá me conecté mal al link. Me conecté a otro con o sea, no me sale como entonces, sin posibilidad de escribir en el chat. Me sale como chat. Ah, perfecto. Ya le hice. Y el audio.
Yeah. Okay, so we'll figure that out and then show it a little bit later. So what I'll go through very quickly now, just some basics of the model so that you see some of the results, scenarios, etc. You'll know a little bit about what's behind that. I was asked to speak more loudly, so here we go. So this, of course, will be covered in much more depth, but the idea is just to give you an overview at this stage. So essentially, the CGE model itself, it captures all interactions in an economy across economic sectors. Okay. So this is the Open EAM platform. So this is where I mentioned that you can get resources related to EAM, land use time cover change, and ecosystem services modeling. I'll just sit down for a minute here. So you can have a look at this later. It's openeam.iadb.org, but if you search for Open EAM, it should be the first thing that comes up. So we have that video here.
The decarbonization of our economies and sustainable economic development are the challenges of our time. Addressing them presents policymakers with tough choices. Complex decisions involve costs, benefits, and trade-offs. Transparent and integrated frameworks are required to shed light on the impacts of public policy on the economy, society, and the environment. Standard analytical tools, however, typically focus on just one dimension of sustainable economic development, leaving policymakers with incomplete information on inherent trade-offs between policy goals. The Integrated Economic Environmental Model, EEM, was developed to fill this void. It analyzes impacts on the three dimensions of sustainable economic development. EEM captures the interactions between all economic sectors, households, and the government. It is used in future-looking scenario analysis to examine the potential impacts of public policy and investment. The value added of EEM is threefold. 1. It integrates natural capital accounts with the system of national accounts used by all countries and generates the indicators ministries of finance and central banks are concerned with. 2. It goes beyond GDP to provide metrics of changes in natural capital, future ecosystem service flows, and wealth. 3. It reveals the spatial dimension of policies, as well as the impacts on ecosystem services that lack market prices. EEM models have been developed for countries all over the world, with a particular focus on Latin America and the Caribbean. For example, EEM was applied to the Amazon region to understand the impacts of moving towards a tipping point and what portfolio of policies can help us avert one. Take some time to explore the EEM platform, where you can access use cases, models and data, user guides, publications, and courses.
So there you have that. Here on the policy impact page, there's three summaries of some applications we've made with the integrated framework. On the building capacity page is where you will find a course for EEM, both in English and Spanish. So it takes you from the basics of CG modeling, social accounting matrices, the data that underpin CG model, all the way to applying EEM with the interface ISIM. It's definitely worth checking out if you are interested in getting more hands-on practice on applying EEM. There's also, for the land use land cover change modeling, there's a video tutorial series that we developed with colleagues at Amsterdam Free University. The video tutorial is quite excellent. If you watch it, you'll be able to implement this model, which is pretty nice. And then we have here ecosystem service model data packets we haven't quite got to yet. You go to the EEM model data and repository, you'll see EEM modeling data. So EEM is programmed in GAMS, the General Algebraic Modeling System. So you can implement it directly in GAMS, or you can implement it through ISIM EEM, which we'll be learning more about. So the coverage is shown here, all the way down from Mexico to Tierra del Fuego. In terms of land use land cover change modeling, aside from the video tutorial, this link will direct you to Amsterdam Free University's website, where you can freely download the model, user guides, and other information. Then we have an application that you can work through here based on an application in Colombia. Then we have ecosystem services modeling data packets. But first of all, of course, we have the link to the Natural Capital Project, Stanford University's suite of ecosystem service models, the INVEST models. You can go there, and they have a phenomenal user guide and many resources to help you learn about ecosystem service modeling. And what we've developed essentially are data packets for 4 of their models so far: erosion, carbon, vegetation, and one more. So if you go to these data packets, so again, we have full coverage across Latin America, and what you'll see there are folders with all of the geospatial information that you require to run each of these 4 ecosystem service models. So previously, just like with the CG modeling, this replication of effort, building the same model over and over again, this was also happening in our service modeling space, where people were using the same data again and again to parameterize these models. So we've circumvented a lot of that effort that's required to run these models now by making these data packets available. It's what we use as a starting point for our Chile application. It saves you a heck of a lot of time and money if you need to pay for the work. So that's that. Now, my new skills here on how to work this. Yes. So a quick overview of what a CG is, and I'll show a short application to Guatemala and the Sustainable Development Goals. So as I was mentioning, CG models capture all interactions in an economy across economic sectors. So they include direct and indirect effects. So if you have fiscal policy that changes the tax structure, you have households then that have changes in their income as a result, you have them purchasing more or less of a certain good or service. And so these second round effects are captured in a CG model. It's a system of nonlinear simultaneous equations representing agent behavior. So the underlying data framework is a social accounting matrix, which is a statistical representation of the economy. And the equations in the model essentially show you how agents in the model interact and transact in that framework. So the main database covers all transactions in an economy. As I mentioned earlier, it's based on the system of national accounts, supply and use tables, especially. So there will often be different years for the system of national accounts will be offered every year, but a full set that includes these supply and use tables, which are critical for CG model development, E model development. They're not offered every year. Sometimes they're every 5 years, but that's a critical input into developing one of these models. And the dynamics are related to investment and savings, population growth, and potentially changes in natural capital. So the analytical workflow is very similar to what I mentioned in the ESM framework, where we have a baseline. It's our counterfactual to which all scenarios are compared. So often, almost always, we're showing GDP in millions of US dollars as a difference from baseline. So it's showing you the specific scenario-based impact of that scenario. Or we'll show in percentage change, etc. We have our policy scenario. So in the NDC case, implementing specific policies and comparing those with the baseline. Then we analyze and validate the results. So sometimes the scenarios that we implement don't turn out exactly as we thought they should. We have a look at the results. We see if anything needs adjusting. And then we proceed to analyzing the results and often establishing a transmission pathway. So this is usually helpful to understand how the policy shock is moving through the various aspects of the model. So if we're changing the land endowment, for example, this would then affect how much land the forestry sector is using, how much land the agricultural sector is using. So we trace this transmission pathway to ensure that the way that we think the scenario should be working, it is working in that way. Or if it isn't, we can explain why it isn't. And it makes sense.
For the baseline scenario, you are imposing exogenous trajectory for the GDP, right? But how do you get the fixed point between, because of the interaction between the economy and the environment or the natural capital, given this exogenous trajectory? So in other words, we have a high growth of GDP, but that implies an important degradation of the natural capital. So that high GDP growth rate is not going to be sustainable, right? Because you are not going to get the ecosystem services in the future that you need to sustain or to support that path for the GDP growth rate. So how do you get this consistency between the economic or the exogenous with the environmental?
Yeah, so just in a standard baseline projection we have, so GDP is exogenous. We will have factor productivities for the sectors endogenous. They adjust to meet that GDP target to convey. We typically avoid doing things that are more complex than what a standard baseline involves. So that we can differentiate what we might consider to be a scenario from what's our baseline trajectory. That's not entirely clear, but what I'm trying to say is that if we want to model some decline in the resource base, we probably do that as a scenario rather than as a baseline, because then we're able to say what the economic impact is of that resource decline. So tipping points example, the Amazon tipping points example is a good one in that regard, where we have this generic baseline where we're projecting GDP growth, labor force, and that's almost it. And then we're showing a situation where there is climate change and environmental decline. And that's called our tipping point scenario, which is comprised of various scenarios, sub-scenarios, you could say. So then what this allows us to do is say that in Amazon tipping point, the impact on some projection of the economy is this. Otherwise, we're unable to differentiate what the tipping point impact is from policy impact. That's how we would model that sort of scenario. We would treat it as something that we do in a scenario rather than unless there's a real reason to do it.
And follow up, I mean, this is a question that we talked a lot about with Gonzalo. If you see the socioeconomic pathways that underpin the IPCC, for example, many of those socioeconomic pathways are not internally consistent. There's no fixed point built, right? Because the job of the scientist is to ask the economists and people who are demography to feed them exogenous scenarios, and then the scientists tell you how much the world is going to warm up. And in some scenarios, it warms up by 5 degrees. So basically, the baseline, I'm going to call it in that case, is a scenario where we have 12 billion people by the end of the century, and the world has warmed up on average 5 degrees Celsius, which is obviously inconsistent, right? Because with 5 degrees Celsius, one thing we won't have in this earth is 12 billion people. So I guess Gonzalo's question is related, because when we talk about the baseline is not necessarily a fixed point, not necessarily internally consistent. Like baseline meaning, guys, let's keep on doing the things we've been doing so far regarding nature. And let's say I'm having 10 or 12 billion people by the end of the century and much more CO2 in the atmosphere. And that's our baseline. And that gives you some GDP growth. But it's artificial, not really a fixed point.
Yeah. Yeah, so with the SSPs, I mean, this is where I think mixing baseline what is the policy intervention then on top of that? We haven't used SSPs, but I have some familiarity with it. I found in a CG context and difficult to manage because of that. It's difficult to distinguish what you're considering sort of this generic baseline that we use as a counterfactual, and then the scenarios themselves. So, the way that we've thought about it in the past, it's worked for the applications that we've had, is that in the social accounting matrix, the implicit assumption is that the environment has been degrading over the past however many years. That's built into the social accounting matrix already. And then we're projecting that forward, but those drivers are still there and they're still happening. That's how we've dealt with it. But on top of that, if we then say, okay, well, the temperature is going to increase by 1.5 degrees Celsius, that's going to imply a greater than baseline sort of change, have impacts that wouldn't be captured in our base representation of the economy. Then we'd handle that in a scenario where we can model explicitly what that means. So 1.5 degrees Celsius, what does that mean for human labor product? Else, and we can be very explicit about it. not have this entanglement between, this mixing of baseline and scenarios.
One comment regarding that, the way that the way you're trying to build on maybe the baseline scenario that usually is confounded with the most likely scenario. Because the way I understand the baseline scenario in this kind of way is the scenario that will happen in a world where resources are limited and temperature doesn't matter. And that's not the most likely because that's the way we are always doing. But we're not considering all these parts. So maybe the most likely scenario is that, and then you put the natural resources on it the same. We find the fixed point that's probably less broad. This time, I don't know, the world ends before that. But the baseline is not necessarily the most likely. So just incorporating the base scenario for environment and capital resources and all that stuff, that will, it's not like a sensitivity. It's like, this is in a world that is perfect, that we don't consider all that. Then we do, okay, but we do consider all these natural restraints. This will be another scenario. And then on top of that, you can do, okay, this policy or this other policy. Because the baseline is you ask somebody that's not taking into consideration the natural interactions, then they'll give you a scenario in a world where there's no natural interaction. And that may be a baseline, but it's not the thing that you think it will happen more likely if people do what the model said that you will do. So maybe it's kind of like find what you mean with baseline, or it is a baseline.
Yeah, I agree with all of that. I mean, I think that as I speak to this generic sort of baseline that doesn't make too many assumptions about the future. So the idea is to model, maybe we use the word baseline in CG, but in other disciplines or in other focal areas, the use may be more of baseline means what we expect to happen without change. So I agree with that. But as you said, to some degree, some continued degradation of the economy is assumed. And a critical question there is also the projections that we use. So if we're using the IMF outlook projections for GDP, are they factoring in climate change into those projections or not? That will also inform what your interpretation of that baseline is. Similarly, with population projections that the UN are coming up with, those factor in climate change, natural disasters, etc.
They don't.
They don't. The IMF's GDP projections don't.
Take that to them. They don't factor in.
The central banks.
We have absolutely zero models in nature, so I'm sure that we're not factoring in nature.
Right. Okay. Well,
No, it's a good discussion. I mean,
yeah.
maybe we should call it the naive baseline scenario. The scenario where nature is not binding.
Essentially, let's think about that.
Maybe there are some features that nature degrades and it affects it.
Building up to basically yeah, I think it's a good point, and how we've dealt with it again is this this modeling artifact, which is essentially that tipping point trajectory, which aims to incorporate those features that a generic baseline doesn't.
We have an online question. It's a little bit different topic, so please feel to defer if you're going to treat it elsewhere in the course. It says, how does the IEEM platform work with marine affairs and marine ecosystems?
Yeah, so in terms of the EAM, the economic model, in a standard CG model, you'll have a fisheries sector. So you're capturing fisheries sector outputs if you had policies specific to the fisheries sector, it would affect activity in that sector. In terms of EAM, we have, as I mentioned, these natural resource modeling modules where we can simulate changes in catch per unit effort, sustainability, quotas, and other policies you might think of for the fisheries sector. From a spatial perspective, we've been looking at it more in terms of coastal protection and not so much fisheries. But yeah, I mean, it's something that we could look at in the future.
I mean, a very good question. What do you think, or what is your guess about what we are losing because not having agriculture? Thinking, for instance, yeah, the active point in the Amazon, you can think of that as a disaster, right? Happening that is going to be maybe low, but for sure people close zero, right? So in a typical math model with agricultural certainty, agents are going to take their decisions trying to avoid that scenario, right? And decisions. When you include that scenario with a probability different than zero, when you know. What is your sense of how important could be that feature in this kind of model, thinking that there is a lot of uncertainty related to the future or the nature?
Yeah, so we can, of course, do sensitivity analysis. Which personally, I haven't found it to be very interesting. So we just shift things by 10% up or down. And you can infer what impacts might be. Modeling time horizons we look at are 2050, maybe 2070 is stretching it or not to. But 2050, when you're thinking about the discussion we had a lot in the context of that study, and now we're working on something similar in Thailand. Do we expect that tipping point to be a falling off sort of example that's often given, eutrophication of a lake, right? It's a very sudden sort of thing, no more oxygen, everything gets killed. We expect that in Amazon tipping points sort of environment. Once you start to try and model that in a quantitative sense, you see that it happen from one day to the next. So, given the timelines that we're running simulations, we can often avoid some of these big. I mean, for many of these things, like the Amazon ecological thresholds, they're suspected to exist, but knowing exactly where they are, when they'll happen, is 1% of science. So, I mean, we can look at sensitivity analysis as one way of dealing with it. And we can look at different scenarios, change households' expectations about the future and as a result of making decisions. We might deal with that in a scenario as well. I'm going to burn through this here so that Justin has time. So I'm just going to wrap this quickly. I won't go through the application today, but we have time, perhaps tomorrow, to do that. The red circles indicate where we place the most attention on in terms of environmental modeling modules, for example. Activities are economic sectors, we have commodity markets, factor markets, satellite accounts to capture things like emissions, water use, stocks of suspended forests and land, etc. So what this is showing here conceptually is the circular flow of income within a CG flow. All of these agents or institutions in the model are interacting through these transactions, and their behavior is conditioned by the equation in the model. So economic sectors, they produce commodities, but they also purchase commodities as intermediate inputs, production processes. They purchase capital, labor, land, other natural resources from factor markets. Households, of course, they sell their capital and labor to factor markets. We have interactions between governments and the rest of the world. This is household taxation and transfers. We have investment care. So as you start to think about simulations, this is a useful sort of image to have in your mind in terms of what is it that you're modifying in simulations that you're implementing. This is the basic data structure of a CGE model, which is a social accounting matrix. The easy way to interpret this is just thinking about it as payments from the columns to the corresponding rows. So we have activities going from the top left to right, activities, commodities, factors, taxes, household, government, savings, investment account. So activities, for example, are making payments to commodities, which are intermediate inputs in productive processes. The purchasing factors of production from the factor markets, they're paying activity taxes to government, and then they have a final. And of course, there are different transactions between different accounts in social accounting metrics. So types of policy questions, we'll get a better feel for that as we move through the week. And then in terms of results, we have an extensive reporting system that we've built over the last 5 years that enables us to develop standards reports.
I see. Thank you. If the EM has a climate model, or it can interact with a climate model?
It could be made to interact with climate models.
The precipitation, wind, or just the temperature is like, we have to think about like a satellite accounts or something like that.
Not necessarily. So we capture, so I mean, you mentioned precipitation, temperature, etc. In terms of spatial allocation for land, those are considered the drivers of demand for land. So we have those soil types, distance to cities, transportation times. We'll go over that on Thursday. But, determine the eligibility, the suitability of each person for based on all of those factors. That's one way that we capture climate. Other way would be through implementing shocks into the model itself. So looking at the literature, 1.5 degrees is going to mean X for labor productivity. We implement that as a shock. We did that in Latin America, for example, to get key effect on workers. So we'll go through results as we move through the week. And so this is essentially what we're capturing with the standard, even without the spatial dimension here. So provisioning services, providing raw materials to the economy. The environment here on this side is represented by the system of environmental accounting. Have provisioning services going to the economy. So the term they use, provisioning services, regulated services, cultural and recreational services. Provisioning services are typically those that have they're used for productive processes. The economy kind of finds waste emissions back to the environment. Hopefully at the same time, investments in the environment to improve environmental quality, protected areas, etc. This is what we capture with the team without the ESN part. And so I'll stop there, and we'll figure out another time to show this application of SDGs in Guatemala. Thank you.
Excuse me a second while I get everything set up on an audio visual sense. All right, well, thank you so much, O'Neill, for a wonderful way to kick off this training. It gives a great overview of, I think, the whole set of interconnections between this new field of connecting macroeconomic models with ecosystem service models. And so what I want to do now is take one of the components of that larger set of interconnected models and dive into them. So this will be focused on just the ecosystem services models themselves. Now, many of the questions so far have been on sort of the broader set of questions, like how does climate change fit in? How do we regard what is the best baseline? We'll get to those. At the moment, we're going to start from the smallest thing and build larger. So this is just how do you calculate the provision of ecosystem services, but it's foundational to the linking of these two different disciplines. So, and can my screen be seen online? That's one thing I couldn't figure out. It is. Okay, we're good. So what will I talk about here today? We've got 3 hours. This is the longest continuous block of ecosystem service training I've done. Usually we have it spread out over multiple days, shorter blocks. So I hope you all have stamina. The overall agenda for what I will talk about is I actually want to start with just a discussion of the overall concepts of natural capital. Yeah, question?
We're gonna have a break, a coffee break at 11
Wonderful.
for 15 minutes. So
Good, that will give me some time to recover my endurance and voice. Looking forward to that. So good, so that'll be somewhere in there, and you'll maybe just interrupt me if I get too into the flow of things and forget about it. Great. So I'll talk about the general concepts of natural capital and ecosystem services. Then I will discuss the Natural Capital Project, an organization I've worked very, very closely with for the last 11 years, as well as the tool that they produce, which is called Invest, that we've already talked about. The bulk of the time then is going to be a hands-on session where we will actually run 3 of the Invest models. And so in the invitation to this workshop, you should have received some information about what to download, and everybody's got their laptops out. This is great. And so hopefully you've already downloaded Invest and you've already gotten QGIS up on your computer. But if you haven't and you want to follow along, this is when you can do an emergency multitasking job of get it installed quick. But yeah, but you can refer back to the invitation for those materials, but we'll be using them heavily. And in particular, we're going to run the carbon storage model, the sediment retention model, and the seasonal water yield model. And when I go through each of those, we're going to jump back and forth between a discussion of the theory behind each ecosystem service, like what are we calculating? What is the science there? And then the actual running of the software that will calculate this for us. And if time, we'll also have a task that will introduce the concept of spatial scenario generation. And so scenario can mean a lot of things. Coming from the Invest natural capital world, this typically means generating different land use land cover maps, and then using those to help us understand how might a different policy that generates this map result in different ecosystem services. Okay, so sound good? So first off, I think probably everybody here knows what are natural capital and ecosystem services, but I just want to start with a quick discussion of it nonetheless, just so we can be on the same page. So natural capital is the stock of valuable natural resources and ecosystems. If my mouse works. No. And this includes the geology, soil, air, water, all living things, biodiversity, and natural systems. This is like a very broad definition, and it's intentionally so. A theme that I think has led to why ecosystem services have been a useful way of looking at environmental problems is that it works really well with some of the powerful language and tools used by economists. And so the first one of those is that term, natural capital, that we just introduced. It has a strong similarity and almost historical pedigree similar to that of capital itself that we talk about in economics. And economists have long discussed capital and related concepts like technically what is a service? Well, an economist would say a service is a flow of value deriving from a capital stock, right? That's one conception of it. That's a very useful way of thinking and has actually led to the sort of expansion of what is considered capital. Probably human capital is the biggest, most accepted one, is we invest in our education, right? And this makes us a more effective capital input, if you will. So social capital, we have many other types of capital that we start to identify as important to the economy. Natural capital just extends this tradition, and it allows us to talk about natural things using the language that economists feel comfortable with. And so far, most of the time, much of the emphasis has been on the easy to see parts of natural capital. So that talks about things like minerals or timber. These are parts of the endowment of the natural world that obviously give us value. They're easy to see because they pass through a market, so they have a price. But the natural capital approach can extend to things in the natural systems and the underlying natural systems that make life possible at all. This is going to be a little bit harder to see, but before we jump into the sort of hands-on work of calculating ecosystem services, I just want to have an appreciation for how comprehensive this approach is. And so basically, I will argue that natural capital is absolutely fundamental in basically every one of the biophysical cycles that makes life possible. And so if you were in various different introductory courses to earth sciences, you might talk about the phosphorus cycle or the carbon cycle or the water cycle, the nitrogen cycle or the oxygen cycle. So that's a year's worth of introductory courses. But the point is natural capital is fundamental to all of these. And if any one of these cycling systems ceases to cycle, that's going to be something really, really bad. And so in addition to the easy to see parts of the natural world that we can put a dollar value on, there's also these regulating ecosystem services, and we'll talk more about that are absolutely critical for us to continue things as they are. Now, why do I bring this up? It's because it deals with one of, I won't call it a pet peeve of mine, but a thing that I have been asked so many times. What is the total value of nature? That's a hard question. What do we even mean by that? Well, it's got an easy answer. I'll come back to why this is important in a moment, but I'd say infinite. I don't know. That's easy. Let's leave it there. It's equivalent to asking, what is the value of keeping modern civilization around? Well, an anthropocentric person might say, well, if there's no humans, I guess that's all the value that's gone. I think that might be missing some ethics here that we're not going to focus on. But my point is that keeping these biophysical systems going is what makes things like farming, something that we might care about, possible. I always like to keep this graph in mind. This is just the temperature over time, the last 150,000 years or so. And you can see huge swings, huge variability. It's maybe worth noting that this part here is the last about 11,000 years. This is the Holocene. This is when, for whatever reason, way beyond my comprehension, it got a little bit warmer, but almost more importantly, the variability of temperature just really dampened down. You can see it kind of stayed in this Goldilocks zone. But we can see also that it is not typical. Before we had huge variation. And in other words, and of course, the point is, it is only in that relatively flat little area that farming happened at all. And so to me, all these things about the nature mattering for the economy, well, what if it wasn't there? We've never had agriculture systems like we have in our world today that make everything possible in these other states of the physical world. So we should be very happy. But the question then of what would be the value of if we tipped back to a situation that could not have farming? I don't think that's possible. But the total value of nature, given this type of large change, what is it? I'm just going to dodge and say it's probably closer to a philosophy type of question than an economics question. But maybe more important and useful for us is, fortunately, we don't actually need to know the total value of it. It'd be nice if we could know that. We've solved a lot of fundamental philosophy questions. But it's not that important to decision making, which is what I care about. Marginal value, right? Economists here, we think on the margin. Well, that makes it very useful because we only need to look at how does it change from one scenario to another, or one world versus another. And that's what we'll focus on. So the reason I raised this as a pet peeve of mine is the first application that had us link an environmental model to an economic model was explicitly out there to say, give us a number, hopefully a big number, of what is the total value of nature. And we gave them a number that was from a relatively small change in the earth. And so it was a relatively small number. And they're like, can you make that bigger? And led to a very confusing discussion. Okay, so that's the total value question. We're not going to focus on. We're going to focus on marginal values, and in particular, how there'll be a change in the marginal flow of value through this concept, ecosystem services. And so ecosystem services, it's simply the flow of benefits from natural capital to people. And just like with natural capital, ecosystem services uses that language of economics, and so has caught on in a number of different policy circles that are overly persuaded by this way of talking that's called economics. And so, long history of academic and high impact reports, starting with maybe the Millennium Ecosystem Assessment and many others since, have outlined the importance of ecosystem services. And I maybe point to one of the more recent ones, the Economics of Biodiversity, or the Dasgupta review. Maybe one of the, it's a really good, really long document about how ecosystem services and the sustainability of our Earth ought to be considered together. Maybe a syntactic note is that's also illustrating the change in language we've used. Ecosystem services maybe is on the downward slope of how often the term is used, and instead biodiversity is rising. Now, as a physical scientist, if you're that type, you might think biodiversity, that's not the same as ecosystem services. Well, if you read the whole Dasgupta review, the economics of biodiversity, basically 100% of the way that biodiversity affects economics is through ecosystem services. So a lot of these things come out to be exactly the same thing, just different ways of phrasing it. So oftentimes I'm actually switching over to calling it biodiversity and ecosystem services, just to avoid the whole definitional question, which I don't find very useful. Okay, so I want to talk very briefly before we get very hands-on about the theoretical underpinnings of ecosystem services, and in particular, how it's been applied to policies. So this research arises from sort of domain of interdisciplinary science. It looks at socio-ecological systems, SESs. And this is thinking about all the many ways that biophysical systems, which I'll plot here on the left, connect in important ways to human systems. And this also mirrors the sort of evolution of the natural capital project and how we thought about understanding these things. We know a lot about ecosystem structure from data, from remote sensing, et cetera. And we can then think about what is the biophysical supply of things that we care about from natural capital. Going whole hog and accepting the language of economics, we can even think about an ecosystem service production function. And this will express something in ecosystem services terms, not the supply, but the actual provision of services. This is right in between the biophysical and human system. And this is where ecosystem services operate as a useful interconnection between these two different parts of the socio-ecological system. With ecosystem services, though, we often go, but not always, one step farther and say, well, what is the value of that service? And that might be in dollar terms or other terms like number of early deaths, for instance, is another way to put a value on it. But this is going to depend critically on things from the human systems, the human locations, where do they live? A sort of fundamental point that is important to ecosystem services is if the production of ecosystem services happens, but nobody is there to benefit from it, it doesn't have any ecosystem service value. And so an example, if we have pollinator services in the middle of the Amazon, but there's no agriculture around, it's certainly valuable, but from the point of view of expressing the ecosystem service value, that is value felt by humans, that particular pollination supply there is not providing any value to humans. So is that clear? Why is this important? Yes.
But still you have like relations among different ecosystems, right? You have interactions. For instance, what's happening in one ecosystem maybe matters for another ecosystem that is next to it, or maybe it's a little farther. So how are you able to deal with that kind of interactions in the invest model, or we just basically we those interactions?
That's a great question, and if in case the online people can't hear, it was, are these models connected in any way? And yes, the answer is they definitely are. However, from a simplicity perspective point of view, the invest models do treat them as separate services. Some applications have used them as inputs and outputs to each other, but the sort of base way of thinking about them is as separate ecosystem services.
I want to know how do you, or do you think it's possible to like the value of the Amazon in other ecosystems? Because I don't know, the Amazon really interferes with climate. So, for example, so it has an impact on other ecosystems. So when you say that a bee in the middle of the Amazon doesn't have value for humans because it has no direct impact on human life, basically so, because I would think that it has value, but it's kind of indirect.
That's a very good and clever point, and it will give me a chance to clarify, I think, an important point. Is when I said there's no value, I should have been very specific to say there's no pollination ecosystem service value being produced there. But your point is very correct that the good habitat that made that pollination service be there is going to be related to other ecosystem services and other locations through a different ecosystem service, in this case, climate regulation. And so, yes, I was being very specific with the bee example. That particular bee won't benefit anybody else, but the existence of the Amazon itself is fundamentally important to the provision of ecosystem services everywhere else. Yeah, thank you.
Biology was founded as a science based on the discovery of natural selection. Is it included in the models? I mean, like plants, biodiversity, as we're talking right now, changes all the time, especially on the micro level, very fast with any change in the environment. Is that model?
We do not have that model very well, no. At best, I would say we have indicators of biodiversity. There's many very contentious debates about which indicators are worthwhile in this. I guess I would say that is absolutely valuable, but we don't have a very good handle on it, at least not from the perspective of invest. We focus on the ones that are easier, I guess. Any other questions while we're at it? Yeah.
When you mentioned natural capital, you mentioned things like timber and minerals, but also you mentioned that is the Amazon. Do you make any distinction between natural capital, between timber and the Amazon? For example, if you cut the whole Amazon and put just timber, you would say they still have the same value of natural capital, or like an artificial natural capital, something like that?
Yes, I would say we do deal with that question insofar as there is a very big difference between the Amazon as it is now and the Amazon if it were all timber focused. And so I guess the sort of short answer is we would say, well, let's calculate what are the ecosystem services being produced in this natural state versus this human state. And well, having run many of these models, I would know that, for instance, the sedimentation that goes into the Amazon River would be drastically different under these two different land covers. And so that is an example of an ecosystem service that we calculate. And so the broader point here is that a really useful way of thinking about this is let's find out, let's change the landscape so that it has this timber plantation. If there is good enough science, we can often calculate what is the biophysical value that's going to be different in each of these different cases. And that's a good way to value it.
But basically, you separate both of these two types of natural capital.
I mean, I might even talk about that here in a second. I'd say related to your point, the most useful way is just thinking about provisioning services that are marketed and those that are not marketed. And so timber is an example of an ecosystem service, a provisioning service that has a dollar value. We do think about those. We often don't focus on them very much in the sort of natural capital project approach, because anything that has a market value, oftentimes already, we're making decently good informed decisions because that price accounts for the value of it. But there's also all sorts of ecosystem services that don't filter through a market at all. And those are the ones with non-marketed provisioning other ecosystem services for effort. So yes, I think we'll get to that though. And I think this will come out when we start diving into the specific models. So, but it's a very good question to keep central here. Okay. And actually maybe related to that point is the question, why is this important? Why is including ecosystem services important? And basically, I would contend that in the inclusion of the value of ecosystem services often tips the scale on any given question about what policy should we pursue, or perhaps maybe even a specific industrial or commercial benefit from like a project of converting everything to a timber plantation. And so in the world, we often make cost-benefit analysis decisions. And what if we had an example like cutting a large part of the Amazon for timber, where when we thought of all the benefits and compared it to the costs that flow through a market, and we therefore are able to put a dollar value on, we might come to a conclusion that, yeah, it will have some costs, we'll lose some timber. Timber's not a good example, some grazing or some other pollination services. In cost-benefit analysis, it's worth pursuing. However, if we add in everything else that might be valuable through ecosystem services, but might not necessarily be included or represented with a direct market value, such as carbon sequestration or water quality, watershed protection, that can tip the scale to say what looked like a good decision, a good development plan to pursue, no longer is a good idea when you consider this fuller set. So that's valuation, and adding those dollar values for these things that are harder to see but still important has been why I think ecosystem service work has been useful in a lot of contexts. One thing to note is that valuation, whenever you put a dollar value on something, it immediately attracts attention. It's a lightning rod. And it attracts attention from both sides, people who think you're undervaluing or overvaluing the work. And so, I'll just reference that to say that there have been attempts at valuation. Some have been quite controversial. Here's a very early article in Nature in 1997 or so, about what is the total value of ecosystem services. And they found 33 trillion per year. And this at the time was bigger than the 18 trillion total worldwide GDP per year. That raises some fundamental questions, I think. But it also comes back to that question of, we're going to think about valuation, but not in the total sense. We want to get to marginal values. I just want to cite that, is that as soon as you go to valuation, you open yourself up to all sorts of potential routes of criticism. Okay, so that all is the concepts. And I love concepts, but I really care most about making better decisions. And that's where my work with the Natural Capital Project has come in as interesting to me. Natural Capital Project is a partnership of a growing number of institutions, but it started off as Stanford and the University of Minnesota were two academic partners. And then we coupled with the Nature Conservancy and the World Wildlife Fund there. And so it was really fun because it was academics, but it was also NGOs that were doing policy work. We came together to do a lot of things, but probably the one that stood out the most is we created Invest. Started out as an ArcGIS model builder exercise as well. I think a lot of things do. But we've actually invested a fair amount of money in writing high quality open source code. You can go in and see the inner workings of every single model I'll talk about here. But Invest, in short, is a set of open source software tools that seek to understand how can we go from an observed or hypothesized change in ecosystems to a change in the ecosystem services, right? That circle that is right in between the two parts of the socioeconomic system, the changes in benefits to people. And in particular, we have about 20 or so different ecosystem service models. So what I'm not going to do is exhaustively list all of them. You can go to any one of those publications I cited at first, but just a few that stand out is we think about nutrient retention, hydropower production, recreation. So it'll span both marketed and non-marketed goods. Other things like fisheries production, coastal protection, and things like that. And so we have these 20 or so open source tools, as well as a full engagement process where we talk with specific stakeholders or specific policymakers who are interested in, for instance, spatial planning or payments for ecosystem services or climate adaptation. This is actually quite dated chart now of where we've worked, but this is really our foundations. We started with specific countries or provinces, very relatively small locations that wanted to do some sort of green economy planning or spatial prioritization of how they should use their land, and done that in many locations. This has really been, I think, the success of the Natural Capital Project is defining a whole stakeholder engagement process. This would look very familiar to any sort of, I don't know, political science or I guess a decision science analysis is, you have decision, you define your partnership, you define your objectives, your scope. But what's unique is this one step where after we've defined our decision makers and our scope, we need to be able to go from the baseline map or the potential alternate scenarios map and calculate the ecosystem services. So that was a missing part. And so Invest fills that role of finishing this circle of stakeholder engagement to have more informed decisions. So one of the last foundational pieces I want to leave you with is just a thought piece, and I'll return to this, is some of the foundational work that really got NatCap off the ground was thinking about the fact that we can optimize. If we have a land use land cover map, if we think about not just how the world is, but how else might the world be arranged, we can see that there can actually be win-wins. And so we're in an economics friendly audience here. So what is this? This is a production possibilities frontier. I just finished teaching the Econ 101 at the University of Minnesota. And we talked about these, but what do we see here? We're talking about two different goods, just like any PPF. Here we have expected number of species though. And so this one isn't a typical production good, is it? But we sort of can think of it that way because we know what the relationship is between reduction of habitat and the number of species. In this particular application, we ran a complex species breeding pair analysis for different species to see where there would be one that falls below a risk threshold. But then on the horizontal axis, we have a more traditional PPF number, but this is going to be billions of dollars of economic value. So basically, we're aggregating everything that is not environmental, that is the actual output of the economy in this axis. And the sort of choice value, the critical thing here is what is the landscape that gets us to these different points. And this point I here, that's the current landscape, that's the one we observe. And what we see is that there are reconfigurations that are up and to the right. What do we know from 101 is that those are going to be unambiguously better, at least on these two axes, because there is no trade-off you get more of both the species and more of, let's see, economic production. You know, there's other things like maybe we want actually much more species. Maybe we care, we're overvaluing the economy. You could think of those too. But often we focus on these EDCB points. These are landscapes that get more of both. So question is, can we engage with stakeholders to find policies that get us to these improved points? We're about to switch into the hands-on part, but before I do, I want to give a sort of overview of what the typical invest engagement looks like from a data perspective, calculation perspective, because that's the fun part, right? Well, the first is just getting together all the input data. And just like with CGEs, this is a very time-consuming and can be expensive process. And that's why I would like to secondly point to the data packets approach that has been done for many countries now already, is combining all of these data types. And so, you know, land use is there at the top because that's the most important one from a lot of modeling perspectives. But then we have all sorts of other biophysical layers. That's the area in the middle there. And socioeconomic layers that will go into the calculation of the provision of value. Importantly, and most challengingly probably, is we also need those maps for different scenarios. And we'll come back to this. But we don't just want to know what is the value of ecosystem services. We want to know what the marginal value is when something changes. So we'll, in other words, create alternate versions of any one of those input layers and recalculate things. So that's the first step, is just getting the data together. Then what we'll talk about next is taking that data and plugging it into whichever ecosystem service models from INVEST we want to actually calculate. And so here's just an example where we have the water yields model, and that's actually input to the nutrient retention model. So there's a little bit of interconnection among the ecosystem services, or the ones like the sediment model. Once these run, we're going to have actually two different types of outputs. The ecosystem services represented biophysically, like what is the water that is produced and put into the reservoir so that it is available for hydropower production, for instance. Now we can think of that in the physical units of, you know, cubic meters of water in the reservoir, or we could think about it in valuation terms. What is the value of that water now in the reservoir in terms of hydropower it could produce, or the drinking water that it could provide? But this flow going from left to right, there's a lot of things you got to do right in here, and this is the sort of basic work that is an INVEST application. And I'll say this is just INVEST. This is before thinking about connections to the economy, et cetera. So yeah. Let me just conclude this sort of introductory set of comments with the value of INVEST, I think so far is that it's relatively easy to use in new decision contexts. Relatively is a big important word here because you do need GIS skills and all sorts of other things which are not super common. But it has been common enough that, you know, we've got now hundreds of citations from people we didn't even know were running the model. And that's the definition of success, I think, is a peer-reviewed publication that you didn't even know was coming from somebody you didn't even know existed. And that's where INVEST has been successful, is good user's guide, extensive documentation, an online community to get these into the hands of people who could actually use them and do policy applications. Any questions before I transition? Oh yeah, I had a funny joke. If you saw my screen at the beginning, this is my friend Kwavu. He's a famous economist just because of his Twitter feed. But I found this to be, literally this morning he posted this, is we're going to have a little bit of a gestalt switch here. We're going to change from what sounds like good words and things that we all can nod our head to. Yeah, that makes sense. We should, should account for ecosystem services. And now we're going to go from, yes, we can do this. And here he's talking about R, and you can do it, and it's easy, and it's for free. But there's a video, if you search his name on Twitter, this is what it's actually like. It's really hard. This is a hilarious video of a person. Yes, it's easy to wash your clothes, except for what if you have to cut your own hole in the ice and you have your own washboard and stuff like this. And so watch that video. He's a hilarious guy. But any questions before we transition? Yeah.
We're not yet in the part where these affect economics, but does economics affect the provision and efficiency of existing services?
Yes, definitely. However, what I would say is that from the sort of historical way that the Natural Capital Project or other ecosystem service applications have worked is they have either ignored that or thought about it on a one scenario by another scenario basis. But what I would say is that's sort of the agenda, that's the direction we're going. And so hopefully some of the next steps, we're talking about that more directly. Yeah.
Are there biological agents to model? Are there microfounding? Is there like a model that models how the bees behave when you're like, is that there, or is there a connection and is like a friction or something?
Yes, I hesitated for a second on the micro point, but what I would say is all of the different biophysical models underneath the hood here in Invest have deep, different publishing literature pools. And so for any given one, my first comment would be is go to the Invest Users Guide. It will have an in-depth discussion of that sort of micro details, as well as I think what you hinted at, which is, okay, the validation of these models. And it turns out, I don't want to call it easy, but a lot of that is sort of established science, or at least the models for which we've actually created a model, we only really do it where there is established science. And almost always, I'll say that, and then a hydrologist is in the room and they raise their hand and they'll say, yeah, but your hydrology model is so wrong and simplified for the following 10 reasons. And we'll sort of respond back with, great, work with us, help us improve it. But the other part of the answer is our goal with the Natural Capital Project and in the Invest tools is to use science that is relatively well established and simplify it down to the point where a policymaker can play with the results, or actually probably the younger technical person who they employ will actually run the models. But my point with this long answer is that, yes, there is this sort of micro-founding for all the different biophysical models underneath this. There is always room for improvement, and when you get experts in the room, they always have their opinions on why our models aren't as good as they could be. But the answer there is to just incorporate the better models. Yeah.
Costa Rica, last years is that the Bua areas are becoming gigantic golf courses, 7-star hotels. Locals, endowment of dollars, small amount, while foreign investors have at their disposal the monetary supplies of the Fed. So there is no match regarding accumulate the resources given that they are for sale. Therefore, I was wondering, some of the outcomes of this market design make that many towns run out of water, while hotels and golf courses consume most of the water. So I was wondering, how can we use this framework in order to account the disparities that the market may legitimizes some kind of allocation of resources, which may be desirable from a democratic perspective.
That's a great point. And I think the first comment I would have is that this is one of the reasons why valuation attracts attention, is if you put things in dollar terms or monetary terms, you are necessarily biasing the conclusion, if you've optimized on dollars, to care about how much value goes into something. But that's going to obviously be biased in terms of those who have lots of dollars. And so you give a perfect example of this, I guess the hotel industry there on the coast probably does have a lot more dollars. And if you optimize your decision on just producing dollars, yeah, it says those hotels are correct. What I would say is that that's something that needs to be kept in mind, but that you can think about it from the perspective of optimizing on more than just dollars. So going back a couple slides, I would just point to this one and say that you can actually have, and you probably should, consider multiple dimensions of what we consider to be good. And so monetary value is one. Here, what this is highlighting is we put another non-monetary one, biodiversity, but you could equivalently think about that as some non-dollar value metric of something we care about. Maybe it is an indicator like percentage of homes that are receiving adequate water. And then if you add that on your axis, you can now think about the trade-offs between this monetary value from the hotel industry versus something that our policymakers might really care about, is what do the locals feel in terms of the impact. So that's a big answer. I would suggest we table it for a while because it becomes even more relevant when we integrate all these models back into a single joint ESM framework. So let's keep that in mind. Yeah.
Yeah. Just a theoretical question. So, for instance, if we think in this figure, each point is not necessarily in the same period, isn't it? I mean,
yeah.
It could be in different times. So Invest has this ability to also model the time framework.
Exactly. This plot can just compare any two landscapes, but you're right to say that obviously there'll be a sort of a transition path, you could think about it, as we go from the initial landscape I to whatever one. And so essentially, yes, we just say where in this trade-off space would we be at each time through the time series. Yeah.
You have an online question from Cecilia Floco. It is, how did you benchmark and validate your model?
Well, it depends on which model. We have 20 some models, and they have all been essentially validated by the peer-reviewed literature. In that, when we have created an Invest model, there's usually 200 or more citations that support the underlying model. And so I guess the short answer is we haven't. We're just going to go ahead and allow the scientific process to come up with a good enough approach. But that's a very glib answer. I think the real answer is go to the user's guide. It talks about this in depth. Each model, there's a huge and oftentimes contentious literature on how do you actually validate your either your biophysical model or your ecosystem service model. I keep looking at you, but I know that wasn't you. Yeah.
No, so I wanted to compare from the question that I thought one of the big payoffs of the using Invest that you can actually bring the conversation of nature into dollars. So I can give you a different example in Chile. There's this project going on for a part of 20 years now. An iron mine which has been approved and then disapproved and then approved again and then disapproved. And now I lost track. I don't know if it's approved right now or not. And it sits right into a conservation area with a Humboldt penguin and a very rich diversity of marine life. And the discussion is always about penguins versus employment. And what I like about the Invest is that you can actually make the discussion about the dollars coming from the iron plant versus the dollars, because we did a lot of work of translating nature into dollars, that comes from protecting the environment, taking into account many different dimensions. And that's what I like about Invest, because you can actually express in monetary terms. Then you go to Congress and you say, okay, sure, employment, this is the present value of employment you're going to create. But then we use these models that are validated, as you will say. And it turns out that the economic value expressed in dollars is actually higher.
Yes, I think maybe I was underselling myself a little bit with that example because it was a very clear one where you have local rights of landowners being heard. But But yes, thank you for that comment, because it sort of returns the discussion, I think, onto why the ecosystem services approach, and INVEST in particular, has been useful. Is we're going to say we want to put it in dollar values because there really are sort of two different estimates. There's the dollar value of a project where it only looks at what we can see. And that is going to be always biased in favor of the development or whatever. It's really easy to see what the value of the hotel is. What INVEST does is augments that with other values that we can calculate, and yes, in monetary terms. And the fact that it can express them in monetary terms puts it on parity in terms of the debate that you have in your Congress or whatever. And that's where INVEST has been successful is, and in the history of environmental economics, I mean, things like valuing damages from an oil spill or something like that, so the Exxon Valdez. This is, the court argumentation centered on what is the actual dollar value. And so yes, I guess my point is that there are still some things that are not considered, and that's simply because there are parts of what we care about, what is equity, that I think ultimately never can be expressed in dollar terms. And so therefore you do need to think about those things. But on the other hand, the underlying value of INVEST is exactly as you say. It's that, but there are a whole big, large set of things in the environment that we can put a dollar value on, and that this at least gives us a fighting chance of comparing it in a corrected sense of what value is produced.
I wonder what are the reasons why we are in the inner part of the financial. I guess maybe one reason could be that with the existing technology, if we extend the use of what we already have, maybe we could, and keeping the land allocation as it is now, we could do a better job. But another challenge could be maybe we are not having the agricultural sector located in the best or the most cost effective places. So maybe we could do a reallocation of economic activities that we are doing in terms of spatial distribution, and we could go to a point on the frontier. I don't know what is the driver.
Well, you've almost answered the question in the way I would have with your question itself, but I'd say there's at least two different ways to think about this, reasons why we're not currently on the efficiency frontier. One might just be a story of dynamics, is that even ignoring ecosystem services, economies often don't produce at their most optimal level on a traditional production possibilities frontier. One answer that's been given for that is capital hasn't accumulated enough yet to get us there. So it's a growth question. We need to grow our way there. That's sort of the default economist answer to that question. But then you also hinted at another, I think the second, maybe most important way is that, yeah, there's a history here of why we put agriculture where it is, and it probably didn't have to do with putting it in the optimized place from environmental trade-offs. It probably was put there because it was easiest, because it was next to a road, because it had good yield, and that's where I owned the land. And so the other part is we're not at the frontier because we've embedded all sorts of irrational decisions. We expand our definition of rationality to include these environmental things. There's much more to say there, but yeah, that's a good thing to bring up.
Justin, we have a coffee break for next. Is it a good time for a break?
Yeah, this is a great time for a break.
Okay. This is good. So 15 minutes. The coffee is right outside.
Híjole, ajo con será con la hoja de juguete y no con la perra se lo comió. No, se dice que los vándalos lo atacaron. Como que la noticia todas tuyas. Mejor eso que aquí piense que es la perra, porque si no le va a agarrar.
Consumers, yes.
No hay necesidad. Sí, obvio. Pero a mí también me gusta.
Pero no suena. Ya hace calor. A ver, me aprieta el dedo.
Bueno.
¿Cuánto será de break? Después te voy al banco. ¿De tu casa?
No, que tengo que conversar con Agustín un rato de.
Ah, ya, bueno. Yo me quedé aquí estudiando. Macro, como para la otra semana.
Ah, la otra semana ya tenéis pruebas, no examen.
No, macro. Hay una cuestión que no entiendo.
¿Cómo te fue en tus pruebas? ¿Ya te las notas?
No de todas.
¿Qué te dieron?
Tengo de macro y de micro.
My reaction to that is that's not the question to be asking in the first year of a PhD. It's a hard question. It's hard because you're right. That is a good way of thinking about it, but it's not what
Micro la entendí muy bien porque tuve mucho micro.
based on that metric. But I think 5 years of PhD. So I'd encourage you, yeah, this is a great direction to go. I mean, we'll talk about it a little bit indirectly later on in this course. It is just the outputs of our integrated modeling typically expressed in terms of GDP. And that's so it's from the same idea of just sum everything up. But I do suppose you could generate a CGE that maximizes something else, like when you're. It'd be a lot of work, but but it's certainly a consistent and good idea.
Now, our CGE model will require a lot of work.
Yes.
Every single pixel you have cost itself.
Yes. Sorry. Oh.
category 2 or category 1 source local in this context have this simplification for infrastructure, and you can use those estimates.
Claro, tiene que tener lo que me digo, que me al menos. La economista es supuesto de racionalidad, ¿no? Entonces, claro. La media y la varianza y tal vez algún otro, qué sé yo,
Ya todo y eso mañana perfecto todo. Una vez había días
Computador del procesador. Hay que poner zoom para que se pueda ver, ¿no?
Sí, lo que pasa es que tendríamos que conectar el HDMI, yo creo, para que se pueda ver, porque ahora lo que se está proyectando es... Sí.
Como coordina. La cosa es que no sería el modelo, la cosa es que sería el mecanismo presente del modelo que aplicamos para generar. Yo creo que una cosa que uno puede hacer es ponerla ahí, claro, yo en el pico donde sale como más de observación.
Hola, ¿ahora sí me escuchan?
Ahí sí.
Ah, perfecto. Buenos días.
Perfecto. Ya.
Lo que pasa es que yo tengo la opción hay que como le quitamos el toque porque están todos muteados y también lo dejamos
El correo.
No está buena.
Sí, habrá que hablar.
Sí, el equilibrio general, pero está bueno para evitar. Yo no sabía que estaban dando lo UIP y todo eso. Lo WIRP y.
Eso siempre lo hemos tenido, digamos.
Para no pisarnos. O sea, si te lo dan, nosotros podemos dar otra cosa.
A mí me da igual.
Sí, no.
Sí, seguramente no lo vemos como ustedes. Ustedes lo vieran mejor.
Una persona muy
¿Y no hay
alumnos?
No, debería.
¿Alumno, no?
Llega gente a la sala. No, pero hoy día en la universidad, como que fue a dar una vuelta. Los estudiantes.
Ah, en los pasillos, dice así. Ah, es que el bar no queda acá. Está. No.
Claro.
No, este va de clase, me parece. Me parece que van los alumnos de clase. Exactamente. Sí, esta semana está
¿Agua?
Yo se la siento cuando.
Pensé que este era el nivel que quedó por
Thank you. I hope you enjoy the coffee. Now we're going to have Juan Manuel will give up reports from the PID. Juan Manuel, I think we can hear you now.
Thank you. Good morning. My name is Juan Manuel Murguia. I am a natural resources senior specialist at the Inter-American Development Bank, and I'm in charge of leading the opening effort at the bank. We are excited to present this course, which is an opportunity to continue collaborating with governments in Latin America and academia in Latin America and the Caribbean region on understanding the potential effects of investment projects and policy reforms on key macroeconomic and environmental variables. As previously mentioned earlier today, the webpage OpenEam has information about the model, self-learning materials and examples of studies using it. This course also is aligned with other supports that the bank is providing in Chile under the lead of Adrian Vogt, Senior Economist Specialist of Climate Change of the Climate Change Division, assigned at the bank's country office in Chile. I would like to thank all of you for participating in this course on natural capital. The Inter-American Development Bank, through the climate change and sustainable development sector, has participated in the Natural Capital Project through the Climate Change Division's Natural Capital Lab, and on the development and implementation of OpenEam, the Integrated Environmental Economic Model by the Environmental and Rural Development and Disaster Risk Management Division. We have used this tool to also evaluate potential outcomes from projects, investment projects, sectoral projects in agriculture, in environment, in transportation, you name it. And it helped us to connect sometimes sectoral analysis with in a language with the Ministry of Finance that is easily understood. Finally, I would like to thank the colleagues of the Central Bank of Chile and the Catholic University for organizing this activity. Thank you, all of you, and enjoy the course.
Right. I'm going to sit down for this one if that's okay, because there's going to be a lot of computer work on my end while we try to jump between the slides and also you running the stuff on your computer. This is always a bit of a dance. How's that? Whoa.
It's a fixed point.
There's our fixed point there. Okay, let's stop that. You okay? Yeah, I'm okay. That was just a fun with Infinity Mirror. Great. So here is part 2 of our agenda. We're going to talk about the first INVEST model, which is carbon storage and sequestration. And so for this small little subsection here, I'm going to first introduce the theory behind the carbon model. And we're going to use it then as an entry point into learning sort of overall way that INVEST models work. The carbon model, the theory is extremely simple and the model is extremely simple, but it will help us understand how to do this type of modeling work. And then throughout, we're going to be doing this simultaneous hands-on exercises. I'm going to walk you through the carbon model as well as QGIS for visualizing the results. And so maybe a bonus goal that you didn't know was going to be an outcome of this is you're getting a crash course in GIS and visualization skills. And that's simply because if you don't visualize the results, what is the results of INVEST? It's a folder of geotiffs. And that's not super fun to look at if you can't actually open them up and look at the maps. So that's a bonus. All right, so this model here is relevant in a lot of things that have already been discussed here. Carbon markets, the NDCs that O'Neill already mentions. I'd also list corporate metrics. Lots of corporations have reached out to the Natural Capital Project asking how can we report on our specific impacts on the environment. Also, targeting payments for conservation has been another area that the carbon model has been used extensively. And then just the overall question of can we find areas that have overlaps, co-benefits between the provision of ecosystem services and other ecosystem service values, or even other things that we value. The theory here, and I again use air quotes on the word theory because it is so simple, is that carbon stock is just going to be measured as a function of what is the land use, land cover in the current state or in some future state. And to first also note, we're going to distinguish between carbon storage and sequestration. So storage indicates the mass of carbon on the landscape that is just present there at any given point in time. Whereas sequestration indicates the change in carbon storage over time. We had a discussion over the coffee hour here about questions like if a forest is there and it doesn't change and it's in its mature forest state, does it sequester anything? For simplicity, we're going to assume no. And that actually matches the evidence probably best on average. And so instead, all of the carbon sequestration that we are going to look at is going to be from a difference in carbon storage between two different landscapes, okay? The basic approach for the carbon storage model is to estimate as accurately as we can for a given area the amount of carbon physical, and we even break it down into these 4 different carbon pools of above ground biomass, below ground biomass, soil carbon, and dead matter. And for a given landscape, then we calculate the total carbon present in these states, and that gets us the carbon storage for a given time and for a given land use land cover map. I'll probably say LULC map a lot. That's land use land cover map. Also then calculate it at 2 different times with 2 different LULCs to get the sequestration value. And this is the difference between the two. The sequestration is the one that we attach a dollar value to, perhaps from the social cost of carbon, and that's how we put a dollar value on this particular service. Yes?
When you have to deliver all the CO2 that is storage in that tree, that's the assumption.
I guess that's the assumption. The carbon storage model doesn't model that level of detail, though. I mean, the real answer is there's all sorts of forestry experts who would say what happens is there's a time path in between one steady state and another. And so if you're taking a steady state forest and you cut it down, there'll be all sorts of immediate emissions, and then also the stump decays, and there'll be more emissions from that, but then also something new will grow. And so there's going to be carbon stored in whatever is the new thing that grows. The answer for how we do it in INVEST is we just look at the steady state value of the forestry system or whatever it was and compare that to the new steady state of what it becomes. So we don't look at the transition path, but we do look at the fact that if it transitions to crops, some crops store some carbon. And so we do at least consider that level of complexity, but nothing about the time dynamics of it. So the model inputs then in this simplified way, again, it starts with the land use land cover map. So a very simplified representation of this might just be colored nicely. We have some area that's agriculture, the yellow, some area that's forest, the green, a little bit of pasture mixed in between. And then ultimately, a lot of the dynamics are just going to be, we'll get a change in carbon storage if, for instance, the agriculture expands into the forest, because agriculture has a much lower steady state carbon storage value. Second input is just a table of the 4 carbon pools. And then we then simply assign the 4 carbon pools values that are specified to each of the different colors here, the land use, land cover classes present, and that gets us the summation of carbon storage. Optionally, you'll see the INVEST model in a moment also can consider timber harvest, future land use, red policies, economic data, or uncertainty, but we're gonna ignore many of those. And ultimately, the input-output flow of these models is INVEST has this land use map as its primary input, gets a map as an input, and it has a map as an output. And so here's a map of the current or future, I guess whichever map you plugged in, carbon storage that is present. And so this is, the unit here is megagrams carbon, or also the same as tons carbon, stored on each hectare of land present here. And so if we had 2 different maps, we could essentially subtract them, one from the other, and that would get us our carbon sequestration. And that's the value that we would then put a dollar value on. And if we also have different scenarios, like suppose we implemented a large scale red policy to avoid deforestation, we might not just think about a current map and its carbon and a future map and its carbon, but also some alternative future map and its carbon. And we can compare the alternative future to the business as usual future or whatever to look then at the marginal value of pursuing one scenario compared to that baseline as we talked about before. Yeah.
So the input here is the sum of all the carbon pools, the total, and then you distribute it in the different pixels of the surface?
Close. We'll walk through that, but the short answer is the table says for a given hectare of each different land use type. This is the amount of carbon storage present. And so it's a careful accounting of which land use types were present, and then multiplying the correct carbon storage values. Yeah.
What is the spatial resolution that you are using for this model?
Invest itself is agnostic to the spatial resolution. And it depends on which ecosystem service you're doing, what is a good enough resolution. This application, I actually don't know what it was. When I calculate something globally, I do it at 300 meters. When we do it nationally, we've typically done it at 30 meters, but that's now even very coarse compared to what we have. And so when we do national level work, oftentimes there'll be 1 meter data sets. And failing that, there's at least, and O'Neill will talk about this, very wide scale use of 100 meter land use maps globally available from the Copernicus project. So ultimately, it usually comes down to what is the finest resolution you have, and that either is from the land use map, which is what I just said. The other one is the digital elevation map, and that's going to be 30 or 90 meters. So the point is high resolution. Actually, I got into an argument with a collaborator who said, "Oh, I look at sub-centimeter resolution imagery," and I'm like, "I don't even want to talk to you." So okay, so that's the outputs. Map in, map out, and that's it for theory. Carbon storage is so simple. But that's the point, is I want to dive into the software because the complexity comes in the analysis of different scenarios or whatever. So hopefully everyone here has already installed all of the required software. For me, it's going to be Invest and QGIS. So go ahead and launch those 2 programs now. QGIS takes forever to load. So go ahead and get that started. If you haven't installed everything and you still want to, refer back to the invitation and the setup instructions there. But then go ahead and open them. For Invest, it obviously will depend on where you installed it. If you're on a Windows machine, though, the easiest way is just press your Start button and type Invest. I'm going to do it live, and so you get to see my computer. And there it is, Invest 3.13 Workbench. That's the one we want to open. Oh, yes, I forgot I have 2 screens. Let me briefly switch so I don't have 2 screens. So that I don't hurt my neck. Okay, now we're looking at the same screen. That's good. Because what I want to show you is what we get. When you launch Invest, this is the menu of different, I'm just going to zoom in. I'm not going to do my animations. This is the Invest menu of models or tools. Now, normally, when we do these Invest trainings, and NetCap has really invested in a pretty robust training program, they're usually with smaller groups of people. So this is the point where I would traditionally get up and walk around and make sure that everybody has got it running on their computer. But is anybody just totally stuck right now and confused? Excellent. I actually think the relative likelihood of having everybody launch a program has gone up over the years. Trust us, we had a lot of learning pains in Invest, trying to get the data, get the software. And so I'm going to assume everybody has it up and running now. But do please, even with this larger group, still feel free to raise your hand. Hopefully we'll also be having online comments being monitored and referred up to others or answered by the group wherever possible. So we have a lot more people than I'm used to. So apologies that I don't get to walk around and look at everybody's screen. But do interrupt me where something is not clear. Okay, so this is the current set of Invest models that are implemented. And what I want to mention really briefly is you should have also downloaded the base data. Getting the data is one of the hardest parts of doing ecosystem service models. And one of the things that we've done recently is we have curated a pretty good set of base data for each of the models. And so if you haven't already, click that gear icon in the upper right that brings up the settings. And there'll be a box here, download the base data or download the sample data. So just to show you that live, you don't need to download all of these, but they're pretty small, so you can. I'd say just get everything and download those to your computer. And like it or not, a lot of being good at computers is organizing your files. So I would recommend taking very good note of where do you download this. And I've just named it Invest Sample Data. I've organized here just in my base data, but here we see a bunch of different folders we're going to generate. We're going to refer back to these a lot. So be comfortable finding this folder, just keep it open. And these are what are downloaded. I've already done it, so I haven't even, so I don't have to do it here, but once you've finished, that's what you get on your computer. Anybody not able to get the base data on their computer that wants it? Good competence. I like it. Okay, so that's the base data. Now we're going to launch our first model. And as you might have guessed, the carbon storage and sequestration model here is the one you're going to want to launch. So give that a click. I have all the, so I'm not going to say stuff. I also have it in the slides for posterity, so you can refer back to this. That's why I kind of have duplicate information up here. But what I want you to do is, well, first on Invest, what we're going to do, the overall workflow is to fill in all of these boxes with the inputs to the model. So it's super boring and straightforward, but that's what is going to be the input that we'll work through here. But understanding each of these components is critical to understanding what's going on. So the first thing that we're going to talk about is what are the inputs that we actually have here. And so I want you to go to where you downloaded that sample data and click on the folder carbon. So for me, that's here. Double click on carbon. And this is the data that you should have just downloaded. What I want you to do now, I actually want to look at one of our inputs before we even run Invest. It's sort of, when you have a user interface that's somewhat easy to do, it is easy to sort of lose track of the complexity of what's going into all the different things. So we're going to look at the data sets. So for carbon storage, I want you to add one of the files, in particular this one, LULC current Willamette. Willamette is a basin in Oregon. It's probably the most studied watershed in the world from the perspective of ecosystem services, just because that's where some of the founders of the Natural Capital Project were first deployed. So that's the Willamette Basin. To add it to QGIS, I find the easiest way is to just open QGIS here and then click on your file again, and then you can actually just drag the file over into this part of the layers box. So you see it's this LULC current Willamette. I dragged it over here to layers, and boom, no, we get an error message. This is going to be asking about projections and stuff like this. And wrong one. I'm going to close this a second. So we've added our file here. And unless you got lucky, it is probably going to give you a message like this of, oh no, there are multiple coordinate reference systems. This is almost certainly the most time-consuming and annoying part of learning GIS here. Has anybody learned GIS and struggled with this? Okay, well, we're going to ignore it. We're just going to select the top one. And if you're curious, this is all dealing with the fact that the Earth is actually a globe, and we're trying to view it on a flat screen. And there are different ways of accurately doing that that minimizes distortions. You could take a whole class on that, but we're just going to select the top one and say, use this one. When you do that, we get to a very brief and uninteresting visualization of our land use land cover map. Anybody not get here or is totally confused? Okay, this is where I want to walk through it interactively. So I'm just going to take 3 seconds, answer questions on Zoom, otherwise forward them to me. I just want to see where people are at. Yeah. Oh, good.
Creo que ese otro software. Creo que eso no tiene ningún otro software.
You got a colored version. Nice. Okay.
Hicimos. User-friendly interface computation. Eso no lo estamos haciendo que hagamos. Ahora estamos usando el otro, estamos usando UX.
Already with our partial interactivity, we have two questions that have come up that I already want to clarify for everybody. What? Yes, so I'll do it again and I'll also clarify two important points. And so what I did is we had our invest sample data carbon. One thing that was confusing, this is the first tip, is I have file extensions shown on my file path. That's a .tiff. Many computers by default will hide that. It's very annoying. And so by default, if you don't see a .tiff, it's because the .tiff is hidden. But what's confusing is there's all these other files that have multiple extensions. You want the one that ends in just .tiff. And so if you don't see a .tiff, it's probably the one with no file extension. Okay, so that's the first thing. The second thing is you want the LULC current Willamette. And that's the one you drag over here. Now, I actually think maybe you guys have downloaded the sample data more recently than I have, because I saw on everybody's screen it came up nicely colored. Is that correct? Did anybody get it black and white? Okay, I don't know what the difference is then. Did you download the data a long time ago? No, okay. I actually don't know why it comes up that way, but we'll address that in due time. Okay, so yeah, go ahead.
Is the model sensitive to the coordinate system, or it's just important for visualization? For example, do you need to be careful to have all the TIFs for the inputs in the same coordinate system to run invest?
Yes, and for the online crowd, the question was, does the coordinate reference system matter, or is it just for visualization? In the carbon model, it doesn't matter, but that's because we only have one raster. We only have one geotiff. It does matter if you have two or more. And so invest will give you an error message if you have two rasters that have different coordinate reference systems. That just means they've been flattened from a globe into a flat map in different ways. And that would mean that the results are not accurate, because one pixel is not always right on top of the other corresponding pixel. Fortunately, Invest has a lot of built-in functionality to reproject the data on the fly so that it converts your geotiffs to the right projection. If that didn't make sense, ignore it. That's okay. So yes, so this is our data. I want to show one quick thing for any of you that don't have it colorized. Some of you, I don't know what the difference is, but got a colorized version that is much prettier than what I have. But if you haven't, let me show you just the 101 of how to make a prettier map in QGIS. So this is your layers area. These are where we're going to add all of our data. Whichever one is on the top of this stack is the one you see. If they're transparency, you might be able to see multiple ones. We only have one right now, so indeed we're seeing just the land use land cover map. But I want you to double click the name of this map right here, like that, and that'll bring up the layer properties. Yours might look a little different than mine if yours already is colorized, but other maps in the future won't, so still pay attention. The single biggest thing you can do to make it prettier is go from single band gray, which is my default, to single band pseudo color. So you don't have to do this if it's already colorized, but if you want, you can do this if you're curious. You can choose from different color bars. I'm gonna go to the spectral color bar map, and as soon as you select a color bar, it's going to pop up with values. This just means that anything that is approximately 1 is red, and as we move towards the higher numbers like 95, it'll be more blue, and then continuous colors in between. If these don't pop up here, you have to click this classify button. You could also change these, but for now, I'm just going to click OK, and now mine looks at least a little better. Ultimately, a land use land cover map is classified data. Not classified in the sense that it's hidden, but classified in the sense that each pixel is one classification of a different land use or land cover. But now you have a basic interface. You can zoom in, you can drag. You can see obviously that this is a city. Portland? I don't know what city this is. I really should know that. But you can see roads versus buildings. And importantly, we see in my coloration of the map, we have this light green and yellow is going to be the forested area, and this darker green and blue is going to be the agricultural area. Okay, this is what it probably looked like for you, and so there you have more information. I had to add this manually, but on what the different colors exactly refer to. This is going to depend on the data, and so if you're working at a national scale, you might have very detailed data on what are the land use classes relevant. Like, so for instance, if you're in Costa Rica, you might have different types of coffee plantations. But if you're working at the global scale, it's going to be much more uniform across all countries, and it might just be agriculture, pasture with not much greater detail. Side note, just for you to understand here, what is a TIFF file? A TIFF file is literally just a big matrix, a two-dimensional matrix. So you could think of it as an Excel spreadsheet. And here I've zoomed in on a particular part of a land use land cover map. And then here I recreated it in Excel, and then used the cell colors to actually show. If you haven't done any GIS, it's easy to lose track of how kind of simple these inputs are. They're just a TIFF is literally an image, and an image is just a big matrix of pixel colors, and those colors correspond to different values of land use classes. So like the 90s here would be the woody wetlands over here. So that's all a TIFF is. Okay, so you've already opened the carbon storage model, but now what we're going to do is set up the carbon storage model. And I want you to add that land use land cover map we've been looking at to the invest model. So to do that together, here's invest, here's the current land use land cover map. This button here will probably not default to your right folder because we haven't said anything yet. So here's the hardest part of the whole carbon model is finding the data. And so wherever you stored the invest sample data, that's get to here, and then find the carbon. And we're going to be adding the same one that we just looked at, which is LULC current willamette.tiff, or the one without the file extension if you have those hidden. And so just select it and hit open. So what you'll notice first off is now when I put my mouse in it, I get a nice friendly green check. Invest is so nice as to validate your data for you. If there's a mistake, like some of the models, if you have the wrong projection or the coordinate reference system is all messed up, it'll give you a red box here with hopefully a useful error message, but it's impossible to design for every possible error. But did anybody not successfully get a green checkbox here? I'm going to take a pause here and just see what problems have come up. Anybody else?
I got out of the green. Oh, no, it's okay.
I know what you're saying. All right, as I said, the competence is high with this group. The only caveat that I should have been clearer on is you have to click in this before you see the green checkbox. And so give that a click, and if you still don't get a green checkbox, yell out, okay. Yeah. All right, so look, congratulations, we just put our first input in. And so now to finish the model, we just need to finish all of the other inputs. So let's walk through those. And so the next thing we'll do is are going to set the workspace of our model. And so what the workspace is just a folder that's going to save all of the outputs. And so for here, we're going to click on this. Hopefully now it's at least pointing to the carbon directory. And I want you to create a new folder called results. For me, I just right click and go to new folder, or however you want to. And we're going to select that folder, results. And we got this time the green checkbox did click up already. It depends on the validation method. And this is just saying that we can write all of our results to there. Anybody? Everybody's good, right? The last thing we're going to add before we can run it at least once is that is the carbon pools Willamette biophysical table. So this is a term we'll return to many times, but here it's called the carbon pools input. It's also sometimes called a biophysical table. And before we do it, I want to actually look at it. And so here, let's go back to our folder of base data. And you'll find in here, there's a carbon pools willamette.csv. Here, we're not going to open it up in QGIS, although you could. I'm going to assume that everybody has Excel, which is great. And I want to look at what we've got here. This is the carbon pools that I mentioned earlier is for each different land use land cover type, which are these ones here, we're going to specify what is the tonnage of carbon present per hectare in the above ground, below ground, soil, and dead matter carbon pools. And so thinking more carefully, what that means is, so residential low density has 15 tons of carbon stored in above ground. At this point, you're wondering, where do those values come from? The answer, and this is sort of typical of almost all invest models, is from the scientific literature. Is that there are obviously scientists who do a very good job estimating values, putting a tape measure around the tree at the right height, apparently it's 1 meter above the ground, I think, and figuring out how to get from that allometric equations that determine the carbon storage. For now, we're just going to use their science. We're going to be a leech. We're going to mooch in all this information. And we're just going to say that our best approximate of the evidence for our area for this particular class of residential land use is this set of values. And we do this then for all of them. Sort of obvious thing you see is that forests are, spoiler alert, good at storing carbon. And maybe the last thing I'll point out here is we have this column over here. This is actually the most important one, the land use code. What we're going to be doing is essentially taking these numbers, and I always think about it as like painting by numbers. We're going to paint this value on the grid cells that have these different land use codes in the LULC map. So if it had a value of 4 in that map, that's a bad example, it's going to get 0. If it had a value of 5, it's a vacant lot, and we know those kind of grow back a little bit, so they get a little carbon. But we're going to do that for all of the different land use classes. Any questions on that? Yeah.
Is it related to what surface? For example, invest automatically adjust if you have another extent in a TIF, for example, 30 meters or 300 meters?
So the different resolution, you mean?
Yes, but this is for how much surface of that land use?
This is for 1 full pixel of that land use. And so, for instance, if you had 30 meter data, and we said it was, this type 1, we're saying that that whole 30 meter by 30 meter pixel is all the same cover. That obviously might not be correct. And so that's where higher resolution maps would do better. At some point, you can get high enough resolution where indeed this truly is only parking lot or something like that. But that just illustrates the importance of using high resolution. Okay, so that was what the biophysical, Neil.
Oh, just to mention, if you don't mind, that if you don't have the carbon disaggregated by type, you could leave it blank and just do 1 for example. So often that level of detail is not available for everywhere. You can just have 1 number in the bulk carbon and not the full carbon.
Invest is designed to be, I guess you could say, modular to different levels of data. It can work with any level of resolution spatially, but it also, right, if you don't have, very few people actually have this level of carbon inventory information. And I'll talk more about it later, but I almost always think about things in terms of what's the globally available data set that we could use here. There it's there's a long science discussion, but Royce and Gibbs is an article that produced global methods. It's called the IPCC Tier 1 Carbon Inventory Methodology. But it is just basically a set of lookup tables for all the different ecofloristic zones, continents, frontier forest status, et cetera. And that's sort of like the worst case. You can always improve from that. That is at least always there as an option. That would be where you get this information.
So in the land use and cover map, you also have like those 4 types of carbon pools.
Not yet. That's what the invest model has. The question was, does the land use land cover map have those 4 pools? And the answer is not yet. What the invest model essentially does is it's going to create 4 new maps, one for each of the different carbon pools that, so we'll say that this is the amount of above ground carbon on this type of pixel. And so then we can have one map that will be just the above ground carbon. Then we're going to do another map for the below ground and soil dead matter.
Okay. Because I was thinking this is related to the condition, right?
Yes.
But you don't observe the condition of the system because you just have the map with the land use and cover map, right?
Correct.
I suppose that later we are going to see how invest generates those 4 different maps. One of each.
Yes, we'll see that.
So for the folks online, could we make like a very brief summary of where we stand now? Like how did we get here? Some are a little bit lost.
Yes, catching up the online folks, and it's hard because I can't see your screens. Actually, the first year I taught at my current university was during the pandemic, and I had to do a lot of these things online. It's not impossible to look at 30 or more shared screens. I know that. What you should have done is opened up Invest, and all we have set is so far 3 of the different inputs. Let's look at it dynamically. I guess I haven't done it yet, so you should have set your workspace folder to be something that you want to write your stuff to. You should have set the land use land cover map here. And then I guess the last one that I've told you to do, but I haven't done myself, and so I will illustrate it, is we are going to point the carbon pools input box to that CSV that we were just looking at. So now when I click on that open box here, it went to the results folder because that's what I was looking at last. Go up a level to carbon. You want to select the carbon pools willamette.csv. Like this. Were there any specific questions from the online group?
No, just.
Okay. Well, and if you're online, please send out specific questions. We'll deal with those as those come in. That'll be the best we can do here. Okay, anybody in the room not get to these 3 checkboxes? Okay, well then. So we did this. Okay, so now, next most challenging step is click the run button. And it'll start to do a whole bunch of math. Essentially just raster math, multiplying values from that table to the land use land cover map, and you can follow along. It'll have some diagnostic information out here. Mine calculated in 39 seconds, or 0.39 seconds. Anybody beat me? Yeah. Anybody not get to where it says model complete? Okay, so we're going to take a pause here, and I'm just going to check on people's screens that we're all done here. This basically means Invest is now finished running, but we're going to interpret this. I just want to make sure everybody gets to this point. Oh, you're good. All right, everybody is at a good position, it seems. And, just reflecting for a moment on sort of data science, there's a lot of stuff that just happened. There's a lot of Python libraries that were loaded onto your computer, GDAL, C++ code has now been run, and you didn't have to know any of that, and that's awesome. Somebody else knew it. And what Invest does is it just tries to simplify all that down. Like, as somebody who has done all the sort of back-end calculations and written the C code and stuff like that, it's really hard. O'Neill, have you ever done that? Well, whenever, like, that's similar with EAM is that, it's packaged in such a nice way that oftentimes you have users successfully do a run of EAM who don't understand the blood and sweat and tears that went behind each of those numbers. So that's a shout out to colleagues past. Okay, so what have we done though? it's, yes, it took just a second, but click on the Open Workspace button. It'll actually open the folder that has now been containing all the results that were generated from this matrix math that we did. And mine will look a little bit different because I've run it a few times. These are log files, more details of what was actually computed. You can go back to that if you're curious. But let's just jump to the most important one. In this folder, here's what it would have looked. This should look more similar to what you have. You'll see there's some new files, one of which is total C carbon current.tiff. I want you to go ahead and add that to your QGIS layer. And so one thing to note is whether or not you see it depends on whether or not you drop it above or below this land use map that you already have visualized. And so I'll just go ahead and do that. So here's the results folder. Here's QGIS. Well, I've done that in the other order. I'm going to take total C current and drag it over here. I'm going to drag it above. If yours is below, you won't see it. One thing you can do is just uncheck the one above it. And now you'll see the map here. This is going to be a map that now the values don't have land use classes, but instead have the numeric tonnage of carbon present on that grid cell. And so let's make it pretty again. What I want you to do is double click the layer name. And under the symbology tab here, sorry, I may have been too fast on that last time. Under symbology, I'm going to make it a single band pseudo color. And I like that one. Got to go down and hit. Actually, I don't like that one. That'll look better for carbon, because carbon is green. Hit classify, and that all classify does is break down assigns different colors, different shades of that color bar that we have. And then once you get that, go ahead and click OK. Now we have a slightly more intuitive to understand map here, is that we can see this is sort of the hotspot of carbon storage. Anybody not get to this point where you have the total C current visualized in a way that pleases you? Okay, we're taking a pause here.
Carlos, es que hay una persona, hay dos personas que están muy colgadas. Pero bueno, son 134, sí, es un montón. Que vale la gente que. Por eso antes le pedí que hiciera no sé qué salió. Le preguntaré a Justin.
Don't worry.
Justin?
Yeah.
We have one person online who has telegraph database is locked because another process is using it error. Have you heard that before?
That's a hard to fix one. So we're not going to fix that one, unfortunately. I would say is if they want to, they can restart their computer. It's just something on their computer is locked down the resources that they're trying to write. It could be their antivirus.
Okay, I'll
It's probably their antivirus.
Thank you.
Okay, so congratulations. You've all just done GIS basics and have now visualized a carbon storage map. And so, what do we see? This is almost trivial, as we see that the forests, especially certain types of forests in this example, store more carbon. The agriculture, hardly any at all. You can see there's a little bit of carbon storage there, and that's because carbon is present in crops, but not much. You can see features like, here are streams. That's a stream running right down the middle. This is where the resolution wasn't quite high enough to really see the stream accurately, but we have vegetation growing along the streams, so you can see a lot. Okay, but where are we? What have we really done here? Okay, so once we've colorized it, we can then start to make policy relevant statements like answering the question based on carbon storage, where roughly speaking, would it be most damaging to climate change to develop the land into agriculture? And you can see the obvious one is don't do it here. Or also just try to avoid these forests that are particularly high value from carbon storage perspective. Here, I want to take the pulse of the group because we're kind of behind schedule, which is fine. As O'Neill mentioned, our goal is, and we can be very flexible here. I was going to have just an exercise to very briefly take what you've learned here and apply it to a future map. This will take us about 15 minutes. It'll give you the experience of trying to work through other inputs to invest. Downside is we'll have less time for other ecosystem services. Is there a preference in either direction? Exercise versus no exercise? Exercise? Okay, let's do the exercise. All right. So yeah, I guess relevant to that meme that I had about R and how, yes, it's super easy. Look how easy it is. R can do it. Is here you might be having the feeling of, okay, well, I saw you all did just run the model successfully. And so now you're a master of it, right? No. Instead, there's a lot to learn, but at least you have a framework. And so to test out that framework, let's put you at these two questions. I want you to rerun the carbon model. But this time I want you to calculate carbon sequestration. And so you'll note, as I said before, carbon sequestration is the difference in carbon storage at two different time periods. And so if we're going to do sequestration, we need to calculate the carbon storage model again. And this map looks compelling. The LULC future map is what would happen if we knew what was going to happen, right? If we were sages and knew what's going to happen on our landscape. Let's just assume it's correct. And I want you to rerun it with the LULC future map. But let me show you something, is that functionality for sequestration is built into the model. So I just want to point you in the right direction. Here's our results. If you close this, you'll get a menu of all the models, but you can also just go back to setup here. Setup brings us away from the results and back towards the model. One way you could calculate the sequestration is do this again. And if you're clever, you might already be putting a future map in right here. But actually, it's got that feature built in. So you could do it that way, but then you'd have to do some raster math to calculate the difference between two different carbon storage maps. And that's annoying. And so instead, go ahead and enable the calculate sequestration toggle. And once you do that, a new box will be enabled. And here is where I want you to add in the future LULC map that I referenced over here in the exercise. And so that will be this one. Some other things that I want you to work through, and so I'll leave this on the screen, is if we actually want to know, get all the way out to valuation, as many economists here in the room know, we need to know a lot more than just the sequestration. We also need to know what is the price of carbon. You can use your own if you want, or you can use 187, which is the 2021 value used by the Biden administration's $51 per ton of carbon dioxide. Side note, we're measuring carbon, not carbon dioxide, so that's the difference. And I'll give you some other numbers about things you would need to know, like the discount rate, or let's just assume an annual price change in the carbon markets of 0. These are just options that you could play with. Go ahead and put those in and calculate what is the total in carbon change between these two different maps. So what is the sequestration? Try that. And then as an optional question too, suppose that future LULC map represents a policy of allowing logging in that area. And suppose the net present value of the timber would have been $50 million in this new land use land cover map. Using the information that you've generated, can you make an argument one way or another to send to a legislator about whether or not from an expanded cost benefit analysis, this is a good or bad project? And the hint there is when you do run the sequestration, there is going to be a new file calculated called report.html. Click around in that, it may be useful. So I'm gonna go on mute here for a second and walk around and see how people are doing. See if you can get this carbon sequestration enabled. Yeah, there's a question about the discount rate, and I went really fast over that. It is one of the most contentious numbers in environmental economics. And also, if you're a banker, it might look really low to you, that the 0.03 that I'm using here, especially compared to interest rates that we can observe in the market. Without going into any detail other than to say, there's a nice report out by Resources for the Future just last year with a sort of most recent synthesis of the evidence on and debate on this point. They argue for using a 2.5% social discount, social time preference discount rate. So I'm actually a little bit above theirs, but this is going to be lower than the observed market interest rate because we're not considering short-term capital investments. We're considering long-term things, which ultimately boils down to nothing more than a preference for value now versus value in the future.
And the results are going to be very sensitive.
And results will be very sensitive to what value you put on this. The carbon sequestration biophysical number will not be sensitive to this, obviously, but the valuation will be. I had muted myself. Hopefully everything I did was self-explanatory. What I did is I just filled in the invest input boxes with what were the values you should have put in. So you can just look at this and refer to this, but years, price, discount rate, no price change. And make sure you have the future map here. Okay, so what that did is you can click on the open workspace, but question.
The annual price change, you put 1, you first say 0.
Is that, what did I say, 0? You know, okay, thank you. I was thinking it was multiplied. I guess that was in the definition. Side note, I will use this opportunity to say you can click here for more information on if it should be 0 or 1. Side note, actually, I will use this opportunity. We've mentioned it a couple times. Invest has a really nice user's guide. And so click on it here, and we actually embedded it in the model. And so this, you could go out to the website, but we thought that could just point to the right part here. So the annual price change, the relative increase, and this will explain if it should have been a 0 or a 1. And so setting this rate greater than 0 suggests the social value of carbon is less than the value of carbon sequestered now. And so therefore, indeed, it was supposed to be 0 and I'd get funny results. Thank you. That was a perfect segue. I'm gonna
I suppose that what it's showing is that there is an increase in the surface that the city is using, and you are getting like a negative difference and you are losing forest in this map, right? In the future scenario. And then going back to the previous question about the 4 different carbon pools. So there are some implicit assumptions behind the situation, right? What is going on with the condition of the forest, how do you prepare land use, but also the condition of those forests also change.
Yes, so the condition of the forest, we assume it doesn't change. With the exception of if you have a transition from one class of forest to another, which can happen, that will show the degradation that might happen. But oftentimes that's a simplification. Okay, so just to round out this discussion, what I've got here is I've got the 2 maps, total carbon future. And so this is the carbon storage present on the future landscape. Underneath it, I've got the current landscape, and I'm just going to toggle and we can see what happens. So you see high values of carbon storage in the base year. 2050, we had a lot of expansion, and we can see that there's just visually, there's a loss in carbon storage. Somebody asked me, could I open this in Excel? And I thought that was a great question, because on the one hand, yes, you could, but this is about 2 million cells, and so it might crash. But you could, but probably more useful is what you want to do is to summarize the information in a way that's useful and not just a map. Like, what is the total? What is the total amount of carbon storage? And that's actually what this report.html does for you. So hopefully what you're wanting to do in Excel would be done here. And this is the information. It's going to sum up what is the total megagrams of carbon present in the base year versus in the future. So we can see the absolute tonnage difference. That would be then the change, the delta between the two. If you wanted to just look at the delta, you could see this one. That map will plot it for you. But then it also will calculate out a net present value of $649 billion lost out to 2050 in NPV terms. So, question.
Are there internal codes available?
The code of the model itself?
Yes.
Yes, every single line. The question was, is the code of the model available? And yeah, Invest takes the philosophy of being completely open source on everything. And so you can see the raw source code of this model and all of the models. You can even look at the history of the model and how its code has changed over time. But yes, the point is to be as open as possible, because real dollar values are being calculated here, which means that real transactions would be affected here. And so we want to be as transparent as possible. And also that's to head off criticisms. Yeah, there are better ways to calculate things, perhaps in different circumstances. But if you are completely clear on exactly what was calculated, source and data are open source, you at least can very clearly say, you might be right that that would be a good way to look at it. But here's what we actually did, and it's very documented in complete detail. That's just I guess that was more my diatribe. I love open source science. That's critical to doing any policy relevant stuff. Do it right and do it open. Any other questions? Okay, so you all are experts now. But you may have noticed that there are other invest models here. We went back to, if we close this, it brings us back to the menu. You could have hit the home button. And this is going to be the full set of invest models that you might want to run. We went through the easiest one, the carbon storage model, just to sort of introduce spatial analysis, scenarios, future versus current land use, land cover maps. But we're going to try one that is a little bit more complex. And we have 40 minutes. And so I'm just going to do the best I can in 40 minutes. Wait, no, I did my math wrong. We have 20 minutes. One minus versus not. And so I'll talk it through, but the code is open source. We can talk more at other points. And so that, again, referencing O'Neill's goal that he mentioned is to get you pointed in the right direction to know where to look. So go ahead and click on the sediment delivery ratio model. Give you a very brief theoretical understanding of the science behind soil and erosion. There's lots of things that can contribute to erosion and tons of models. And underneath each invest model, just like we've been talking about, there is this large science that there's never going to be uniformity, but we're at least taking our best chance at establishing what are some at least well-known models. And one of those is the one that we use here, is the universal soil loss equation. It's in the basic soils class. You won't be able to read this all, but basically it's more or less a regression that establishes the relationship between things like rainfall, erosivity, soil erodibility, things about the slope, what cover management practices are present, a whole bunch of things that matter and have science supporting them, but shoves it into one equation that is parameterized by a regression for getting the USLE, or the universal soil loss estimate or equation. And that's what the invest model does. There's more to it, but it's basically going to implement this regression for us, along with other things, such as how much of that sediment, the soil loss that happens, where does it go? Does it maybe just get grabbed up by vegetation on the next cell and prevented from going anywhere? Or does it make it all the way down into a reservoir, causing hydropower production to become limited? That matters. So refer to the user's guide if you want much more detail on this. But instead, I'll produce here just a very simplified discussion of what the model does. So here is a very simple land use land cover map. This is 4-pixel straight land country, where it's just one line of pixels on a hill that is going down towards a stream. And so maybe the first thing to know is it's a hill. So if you drop water at the top of this hill, it's going to flow down the landscape towards the river. It's passing through all those pixels. And this is important because if we want to know what happens to sediment that leaves a grid cell, like for instance, suppose this corn, this is not, corn is not very good at holding soil in place compared to like a rich vegetation cover. And so we're going to say a lot of sediment is going to leave this grid cell whenever there's a big rain event. So in other words, a ton of rain comes down and some amount of soil, tonnage of soil is going to be removed from this grid cell and start flowing down the hill. Oh, I'm gesturing with my mouse and you can't see it. There we go. I was gesturing wildly. So the size of this arrow indicates how much sediment is being exported from this grid cell. But what we want to know, if we care about how much of that makes it to the reservoir and affects our hydropower, we need to say, well, what happens in this grid cell that it passes through? This forest is going to retain some of that. That's the whole point of a lot of natural land, is the forest will retain a lot. Maybe some will get retained by the wheat. We can always calculate what is the remaining amount of sediment from this grid cell that is still flowing down the hill and eventually makes it into the stream. But that's just for this grid cell. We'd want to calculate, to make the point, then we can actually calculate the total retention of this cell on these downstream grid cells. But obviously we're going to want to calculate that for all the grid cells in Straightlandia. And so forest doesn't export as much because it's just a forest, but it still does export some. So we're going to account for that all the way down back into the stream. Keep going down the hill, hope that we put a lot in. And then we're also going to say that last grid cell right next to the stream. You'll notice we're keeping track of a lot of different variables here. Like this, we can see this is the total amount of work, I guess, that this last grid cell did. This is how much that grid cell retained from all of the So I highlight that one because this is actually the one that is closest to interpretation as ecosystem service value. But really we're calculating a lot of numbers here. So that's a simple landscape. A slightly more realistic landscape, you might think about something like this. For any given pixel on our landscape, we can divide it into the upstream transport area based on the literal topography of the area. The water flows towards one point. And so this is saying that this pixel here, these are all the contributing upstream pixels that might flow into it. So if we dropped a drop of water anywhere in this orange area, it's going to flow into here, to the pixel of interest. But the second thing it will do is then we can say, and where will it go? It'll be in the downstream flow path. Once it's in one point, then it takes a specific route. And so identifying the upstream area of transport and the downstream area of retention, that lets us calculate not just the soil loss, but the total export by figuring out what is exported and then how much is retained in each one of those grid cells. And that is then calculated for each pixel. But we're working in big data land. So those are very simplified landscapes. What we really work with is satellite data. So here's just one of the critical layers that goes into this is for any of the hydrologically routed ecosystem services. So that would be sediment, nutrient retention, also just water yield. It depends critically on the topography of the area. And that is represented in our model here by a DEM, or a digital elevation model map. And side note, I love space. This was the most commonly used DEMs were literally calculated by the space shuttle back when we had a space shuttle. And it had a 200-meter or something like that arm that stuck out, and had two different lasers from two different perspectives shooting down onto Earth to figure out very precise measurements of elevation. And so very cool stuff, I think. But it gets us a map like this. And because for time, I'm not going to do it, but you could expect, you could maybe do this as a practice if you're super interested, that output, the invest sample data folder contains this exact map. So you could do the same exercise that we just did, drag this into QGIS, give it a nice color. And so this is just going to be a raster of the Gura district of, I think, Kenya. And so the color then will indicate the elevation in terms of meters above sea level. So we get pretty maps like that. And, a couple things, if you're sort of very keen-eyed, you can see what kind of is the river network. See this, there's kind of like it looks like a depression here. We can see the coloration. These, if you've ever looked at topography maps, that kind of looks like what the river does. Here's another spur of the river. And so indeed, this is the Gura River that we can see just by looking at the elevation map, because obviously the river is at the low point in the elevation anywhere on this. The reason why digital elevation is so important is which direction water flows can be calculated from that. So this is one of the big computations. It takes a lot of time. And so why really NatCap, a lot of our money was spent on calculating things faster than we could before. And so being able to quickly calculate a flow direction map, which I show here, is one of those computationally intensive steps. And what this one is this map here is just literally saying what degree, 0 to 360, will the water flow out of a given pixel. And sort of a cool byproduct of it is that ends up looking like a shadow shaded map. That's just what it looks like. And so here we can see that same calculation that we did for a focal pixel. Now we're going to say for this pixel, using the flow direction map, we can see that all of these ones in this thing that kind of looks like a shaded side of the hill flows to here. And we can also calculate where does it go from there. It follows this almost stream-like structure down until it's in an actual stream. And then here, this area that's perfectly flat, this is the reservoir itself. And so doing that calculation for this focal pixel, but for every single pixel on the landscape is why we spend a lot of money on computers. Running this globally was only able to be done in 2019. And it cost us $2,000 of Amazon Cloud compute time to calculate one map of that globally. So just to give you a sense of perspective. But for a smaller region like Gura, it can run on your laptop. So that's the INVEST sediment retention model in a very shortened and stripped down version. But relating that in the last 10 minutes to what we've got here, one thing I'll show that's kind of cool about INVEST is I've actually already run this before because just prepping for this. And so I'm going to load the parameters from a file. Sorry, question now.
The last one, the last tip, it's calculated in the code, or you have to have it as input?
It's calculated completely in the code. And so that illustrates what the workings of INVEST really is you have some input, but it's going to be a land use land cover map. You don't need to provide flow direction. That's what is calculated internally. But then you will have an output map, and I'll show that in a second. So yeah, it skips all those challenging steps in between.
It's like maybe a physical part, like quantitative dynamics. In terms of the services, what are the services that we get because of the sediment retention?
Yes, that's a great question. Indeed, I did skip that. Sediment retention is one of the models in INVEST that doesn't have built-in valuation. The ecosystem service is represented by the sediment retention map. And so that's kind of unsatisfying because it's not a dollar value map. But I'm going to summarize a huge literature really quickly, then also say that we're going to talk about this again in the macro context, is that there's lots of ways to put a dollar value on that. Once you know how much avoided sedimentation happened on your landscape, you can do cost avoided analysis, like how much less frequently would you need to dredge your reservoir. We know how much that costs. And so that would at least be a lower bound on the value of that amount of avoided. There's also benefits transfer, of course. You can just look at other studies. There's a whole huge literature on how to go from tonnage of sediment not put into the reservoir to the valuation. Another one would be hydropower. Obviously, there's a well-established relationship between sediment in the water and reduced amount of hydropower electricity, and thereby the price of electricity. I skipped that for now, other than to say that a lot of work is done. But I'm also inkling towards the future, because what we're going to talk about coming up is not these sort of bottom-up replacement cost type of approaches, but what happens top down when you say, what if that shock is felt by the economy and affects the productivity? That can actually be estimated by GDP, and this will be a big theme we're going to refer back to in upcoming days. Just because everybody is here late, we're going to load parameters from a file. Oh, resolutions. Oh yeah, okay, it looks like it reverted back to you still being in full screen mode. Huh? 1 second. Okay, there we go. Oh, but now I'm not sharing my screen at all. Okay, there we go. Back up. So here is the invest sediment retention model that you could have loaded. And because we've got 7 minutes left, I want to highlight that you can load parameters from a file. After we ran our model, let me show you the invest model. In the results folder, so this is the input. If you go to results, these are all the log files that I've generated. This just is a detailed description of what we calculated, but it's also a detailed description of what the inputs were. And so it doubles as a file that can be used to reopen the model. So I'm going to use that functionality and say we're going to load parameters for the sediment retention model from an existing run. And so here, we don't want the carbon one, but what I will show you is here's all the sample data. Then go to SDR, sediment delivery ratio model. And you should have much of this same stuff. You haven't run it yet though, because so you only have the sample data. I've got a results folder. And importantly, I've got a log file of a successful run. So I'm going to select that file, and it automatically filled in all of the values for each of the things. Had we had infinite time, we would have talked about each one of those just like we did with the carbon model, but just trust me. And instead, I'm going to, just for show, click run. And you can refer back to the recording of this to get which values I put where, but essentially it was saying, here's the land use land cover map, here's the digital elevation map, here's a bunch of other factors. The science is a lot more detailed. And so it's actually, that was quick, calculating a whole lot of stuff. And you'll just refer back to that and or the user's guide. What I want to show you is how to interpret the results, because that's more important. And so when you have finished with the model, your folder is going to look a little bit like this. I will plot some of these because they're fun. I'm going to get a new project because this is a new area. So first, put in a shape file. Oh no, so yeah, so this is the Gura region. And so far we've just been showing raster files, which are just those matrices. Another type of spatial data is a polygon. This is a shape file. But that's where we've calculated it now. One of the useful ones to report would be sediment export. That sure doesn't look interesting. And so this is the where it's really critical now to colorize it in a useful way. And I'll show you a trick where you could do continuous, but I want to do quantile. All that means is when we calculate what color displays for what number value, we're going to have 5 quantiles that each have the same number of pixels. That just makes it a little easier to see. And it works really well. The reason we couldn't see anything before is because we had a couple of single pixels that were extreme outliers. This is actually fundamental to the nature of sediment retention. That's always the case. Why is this? Is because the pixel right before you get into the stream is really important. So this is actually not just an artifact, but the key conclusion of the model is that definitely don't deforest that last pixel right on a big flow path. But here we'll color it with a quantile so we can see it more easily. But this is where there is sediment that was exported from a grid cell and it successfully, I guess, made it all the way into the stream network. And so this would be a function of all those different things like the soil type, was it retained on any of its downstream paths? So you can sort of see things like here. That's just kind of a topological feature here. This is where the water starts to flow fast until it makes it into this white part, which is the stream itself. So that's why this part would be really important to preserve right here. But other things, the last thing I'll show you is we might actually be interested in the ecosystem service value itself. And rather than what is the actual successful export, we might want to ask what is the avoided export. So this is where the soil did succeed at doing the bad thing. But here's where nature did a good thing and successfully kept it in place. Here, I'm actually not going to, I'm going to look at it in continuous values. And no, that's really still hard to see. I'm going to do it in quantiles. This is a map of the ecosystem service value. The units here are, this is the tonnage of sediment that if it had not been natural vegetation, but instead had been bare soil, in this case is the comparison, we'll come back to that. This is how much sediment would have made it into the stream. So if you know, for instance, how much does it cost to remove a ton of sediment from a reservoir that you want to have hydropower functioning better in, you could actually simply multiply that dollar value per ton times the summation of all these pixel values of how much tonnage of sediment was avoided from going into the stream, and you get your total dollar value of ecosystem services. That was the fastest I've ever done the essay. So there's probably lots of questions, but I also want to be conscious of people's time. I guess we're calling it quits from here, but we still have 3 days of this workshop yet. And so I hope this has given you a very specific and in-depth, hopefully useful introduction to what INVEST is, and will set us up for the next few days, which is going to say, okay, that's great that you can do it for a tiny little watershed. What happens when you want to do it and connect it to a whole economy? That's kind of the arc of the rest of this workshop. Thank you.
Well, thank you, everyone. See you tomorrow at 9. No.
Can be done anywhere. It's just the new state is the IDB.
Aparte, yo creo que una pequeña charla de cómo no deberíamos, no sé quién la va a dar. Menos tener una zona que cuando la cancha estudiante listo por
Me voy a
So I can happy to send the slides. We'll kind of blow up. Sure, we'll talk about
Una pregunta.